Yeah, so most of it is self-explanatory, but I'll give you uh, a sort of an idea on how to transform that inverter characteristics into gate characteristics, basically. Um, yeah, that's it. And so we'll get started. Any if has just to kind of since we have a lot of students today, and even though we had half as many last time, uh, because people are familiar with MOS right now, at least the basic MOS operation. So what I'll do is I'll try to go through um, the I'll go through the material as quickly as possible, not like speed through it, but just kind of go through it without a lot of questions. Like we have done before, like interactive, not have it that interactive, but that doesn't mean you can't ask question. Please go ahead and ask question if I made a mistake or there's something which just bothers you, then do it. But I'll try to go through it quickly. Hopefully that'll answer most of your questions, and in the end we can do a Q&A session, which hopefully will be more efficient use of time, at least for this lecture today. Okay, so any questions before I start? Okay, so Mos inverter static characteristics, like as I said, no capacitance. We're just going to deal with voltage, current, resistors, basically. No capacitance, no obviously inductors in most of the IC design we do. Okay, so before I start the inverter, obviously just a formality. We are looking at this logic abstraction where you give a 0, output is 1, or the output is input is 1, the output is 0. But like I've said before, this is what I call it as a logic abstraction. It doesn't have any reality to it. In real, we need a voltage, a current, a magnetic field, a charge, or something like that. So typically it's voltage based. So um, our logic 1 is decided by the voltage VDD, which is the supply voltage, and the logic 0 is decided by the ground, GND voltage. And the ideal inverter, you want the input from 0 to VDD by 2 be considered as logic 1, and from VDD by 2 to VDD input, you want to consider the output as 0 or logic high, input logic high. But in reality, that's not the case. There will be some transition period, and we'll talk more in detail how to define that transition period. Okay, and obviously you can define this as 0 and the ground as VDD, but obviously in order to be able to communicate with different people, you want a standard, and this is obviously a more intuitive and obvious standard. Okay, so I'll start with what's called a NMOS inverter with a load. The load can be a MOS transistor, a resistor, or anything like that. Now this was actually the first gate, the um, first first gate which was constructed as a digital gate, because the first IC processors had only NMOS in it. So the way the gates were constructed was you actually have a load. A load can be usually it's a resistor, or it could be a always on MOS NMOS transistor. So what happens is if this switch is off, so your Vin is equal to 0 or less than some value, then this load will charge this capacitor to VDD, and that's your logic 1. And when you want a logic 0, you switch on this switch so that uh, this is discharged. But obviously, you want this to be much stronger than this because you're always fighting this in case of a 0. Okay, so and that was the main disadvantage with NMOS loaded inverters, and because they are power consuming, because in one cycle or in one state, you're always drawing current from VDD to ground. And that's where CMOS came into picture, where you actually add a complementary switch. So that's why it's called complementary MOS. You added a complementary MOS so that when you're pulling down, you switch this off. When you're pulling up, you switch this on to charge it, but you shut this off, like in this case. So, like I said, when it is on, um, your output voltage is some output voltage VOL. It won't be exactly zero because now you have this thing fighting it all the time. So there is always a residual current through this. When this is off, it is almost charged to, or in this case, the way it's shown here, it is charged to VDD. And that's what's called your output voltage high. This is called your voltage low. Um, and in between, there is this transition period. It's not exactly, the ideal one I showed before. And we'll go a lot more into detail what goes on in this transition period. But before I do that, just a couple of definitions of the inverter characteristics or noise equations and so on. So the first one is the VOH, which stands for voltage output high. OH stands for output high. So that is when the output logic is 1 or the input logic is 0. What is your maximum output voltage? Obviously, ideally, you want it VDD, and in CMOS case, it is VDD. But in some other types of gate, it may not be the case, like a resistively loaded or a MOS loaded transistor, for example. So that's the definition, is what's your maximum output for your logic level 1. Okay, so that's VOH. Similarly, VOL is what's your maximum output voltage for output logic of 0. Again, in this example for case, ideally you want this to be ground because you just want to utilize the entire spectrum of your supply voltage. Not only that, you want to maximize your noise margins, which I'll talk in detail in coming few slides. So that's your V outlet. What is your maximum output voltage, minimum output voltage for logic 0. Minimum you want it ground, but may not be the case depending on the architecture of your inverter or your logic gate. VIL, VIH, again, this will go a lot more into detail, but definition wise, so VIL tells you the voltage. So it's actually, the definition is from input of 0 to this voltage, where the gate considers it as an input low, logic 0. So what is the maximum input voltage for which the gate will interpret it as a logic 0? So obviously, if it is 0, the gate will take it as a 0. But since this is an analog voltage and my output is a digital output, there is a range of that voltage for which the output will remain 1. Okay. And the point where it is calculated is when this slope here with, so V out, dV out versus dV in, that is the delta V with respect to delta V in, delta V out with respect to delta V in. It's obviously 0 here. It'll slowly start increasing at the point when it is -1. When I said increasing, I meant the magnitude of it. So it is 0 here and slowly starts increasing negatively. And when it reaches 1, that's the point you want to stop and say, this is my input logic low. After that, I don't know what it is, but below that, from VIL to 0, I'll consider it as a 0. Why do we choose this number? Again, I'll talk more in detail about that. Similarly, VIH is what is the minimum input voltage for which the input logic is considered as 1. So for example, if your output logic of this gate is VOH, from VOH to this input V in, this whole range here is your considered as your input as high, right? So again, same thing. If you look at the derivative here of this, it is almost 0 here. And as you keep going up, it will start increasing, or the magnitude of that will start increasing. At the point when it goes equals to 1, you stop there and say, this is the minimum voltage for which I'll consider as the input as 1. Above that is 1. Anything below, I don't know. So you have this definition for your input low this definition as input high, obviously this is the region you don't want to be, and that's the region we'll define more. And then the other term we use in digital logic, CMOS logic, is this point, which is called VTH. And please don't confuse this VTH. It's unfortunate choice of terminology, but this is also called VTH, but this is not your threshold voltage. This is the voltage at which your Vin is equal to V out. Okay. So this transition when is happening, there is only one point where V in is equal to V out. And obviously that point is always there, because if I draw this line, which is V in equals to V out, it'll always intercept this line. So there is always this point, doesn't matter which inverter, how you do it, unless you completely mess up the inverter. So that is called the threshold point. And that's also when you're designing gates, that's usually what you design for adjusting your noise margin and stuff like that. Okay, so now I'm going to talk about noise margin. And noise margin is very critical to, in fact, digital design exists because of noise margin. If you didn't have this noise margin, you might as well do everything in analog, not worry about digital. What I mean is that, yes, Puneet, go ahead.
So in the previous slide, I have one question.
Yeah, go ahead.
So in the input side and the
Yep,
input access, so there it is VOH. So
yeah.
it's a VOH, or it's just by mistake, or it's supposed to be VIH.
This one here, you mean?
Yeah.
No, I think that's VOH, because when you're in, oh, 1 second. Yeah, when your input is VOH, well, the reason it is VOH, you're asking why is it not VDD, or you're asking why is it not VIH?
Yeah, so my is like why it is not VIH, because on an input line, so whatever the voltage is here, that's supposed to be uh, out input high voltage, means the voltage for the logic high, that.
Yeah, so this is the highest logic voltage. So for example, if you're using this kind of logic in your entire digital system, then the highest voltage your output will go is VOH. Well, actually, in this case, it's VDD. So in this case, actually, this will be VDD. So that's your VOH. But the VIH is not this, right? Because the VIH is, because here your output is almost flat here. You're like almost the zero gain region. And when you're decreasing your input, you get to the point where this slope is equal to -1. That's the point is VIH. Basically, anything above this voltage is considered as a 1, right? So that should be your VIH point. V
So
input high,
yeah,
right?
so basically VIH minimum and VIH maximum. So this the first one where the
Yes.
dV out and by dV in equals to -1, that is VIH minimum. Am I right?
Okay, so I don't use that terminology in my end. So I use the
Okay.
terminology as VIL as the point, which is VI. In this case, it is V in max, right? This
Okay.
point.
Okay. Okay.
And this
Okay.
point is zero, basically, or VOL. Actually, I should consider this as VOL, because uh, you can't go lower than VOL. So VOL is this point here, because the logic which is connected before me, the input cannot go lower than this, right? And VIL is this point. So this is the region where it is considered as a zero. So same
Okay.
thing.
Okay. Got it. Got
You
it.
got it, right? So,
Yes.
so yeah, in my terminology here in this lecture, when I consider VIL is what you're considering VIL max.
Yes.
And VIL minimum, I just say it's VOL, because whatever logic I have getting connected, it'll just be VOL. But you're right, you might have a mixture of logic. So this might be VIL minimum. So in this case, VIL minimum is actually 0 volts. So it'll still be considered as zero. And in your terminology, this will be VIH max, which is VDD. VDD will be VIH max.
Got it,
So I
sir.
think, yeah, I think different books, like this is the terminology they use in Kang and Hodges and others. So
Yeah,
I
I mean,
just stuck to it.
yeah.
Yeah,
So everyone is using this terminology, but
yeah,
so
yeah.
what I am doing, I'm just using my terminology, just
Sure,
like
sure. It's just,
in a
yeah.
below note also, I mentioned that VOH equals, that is VO out, V out max. So I usually use this particular part. the
Oh, so
second
you
one.
call it this as VOH max. No, I call VOH as the V out max, maximum output voltage when output logic is equal to 1.
Oh, okay.
It's actually the textbook. It's not like I'm saying, it's the textbook definition and I just stuck to it.
Okay, okay,
Yeah.
okay. Thank you.
All right. Thanks. All right. So noise margin, like I said, noise margin is probably the single most reason why we use digital logic instead of analog. Because when we represent in abstractions of ones and zero, like for example, if I have an amplifier, so let's say this is let me order the amplifier here. Um, so let's say I have an amplifier. This is an amp, and this is my V in. I'm giving in this, and the output is V out, right? So in analog sense, V out is equal to some A times V in, right? So whatever appears in V in appears at the V out. So which means that if there is noise, then the noise also gets gained by the same amount. The amplifier doesn't know the difference between signal and noise. It'll just amplify it. But that's the beauty about digital circuit is actually it can differentiate between digital logic and output. So for example, let's say this was a series of inverters connected in your digital circuit. So let's say this is sitting at 0. So this is 1. I'll call this as VDD. So obviously this input is VDD, and this is 0. Actually, yeah, that's fine. This is obviously 0. This is 0, and this is VDD, right? So let's say there is another set of inverters which are actually connected in the same fashion or whatever it is. And this has a clock or some really high speed signal going into it. So output is obviously going the inverted of that. Now, in IC design, there is no point or there is no wire or there is no node in your system which is not coupled to something else with a capacitor. It just so happens that it might be a very small capacitor, but they're all coupled. So for example, from this, there will be a capacitor from to this node, and then from this node to ground, something like this. Like as I said, they vary in sizes, but you're always talking about some sort of a coupling. So this is sitting at VDD, and when this node goes like really sharp, right? And everyone knows the current flowing through this I is equal to C times dV over dt. So this ages the dV over dt is really huge. That means there'll be a huge current flowing through it, which means it'll charge this gap. So this will or discharge this gap because the current is the negative direction. So this is sitting at VDD, and it'll immediately get a glitch, and then it'll go back to VDD, right? Now, obviously during this glitch, or there might be just like power supply noise, you don't want this output to be also responding to it in the same fashion or have a positive glitch like that. Your output should be sitting at 0 because that's not a signal, it's just a noise, okay? And that's the whole idea of noise margin is that because in real circuits, everything is banging around. There's a lot of voltage switchings going on, coupling to everything else. In simulation, in ideal world, we think it's sitting at 0. If you ever probe into a chip, you'll be almost shocked that this thing is working, that everything is just banging around like crazy. And everything, it just so happens that you have designed it for all that craziness and it works. I mean, it still surprises me to date that it works. Okay, so that's the essence of noise margin, that when your input is sitting at low, for a certain amount of voltage dip or voltage rise, you don't want to change the output of that particular gate, in this case this gate over here. Okay, so I'll show it in a diagrammatic fashion. So I'm showing this arrow here is basically showing the output of this inverter. This arrow is showing the input of this inverter over here. Okay, so what I'm showing here is so I've divided this whole range into from VDD to ground. So that's your supply, right? So any voltage inside the chip, unless you have an inductor or some switch capacitor circuit, the voltage is not swinging above or below this. Okay, there's some ringing and swinging and all that happens, but just for practical purpose, for static case at least, without any capacitors. Okay, I told you guys that we won't be dealing with capacitor. I'm just showing you what's the source of the noise here, right? So noise margin, when we analyze it, is still without the capacitor. So don't get confused with this capacitor. This capacitor is just showing you what is the source of this noise. So that's your entire range of your VDD. I mean, range of voltages which are available inside the circuit, right? This output inverter has a certain, we have already defined, the output is going to be, the output high is not going to be, it can be or it may not be depending on your circuit. In CMOS logic, the VOH is equal to VDD, but otherwise whatever is the output voltage high, that is your value here is considered as a VOI. Same thing, the output low for this guy is this voltage VOL. So I've shown this with this blue box here. So you're sitting at here as VOL, okay? And this is your VDD. But VOL is and VOH are the numbers you care about from a noise margin, okay? And for the input of the same inverter, which is like, let's say the second instantiation of the same inverter, the input, like as we defined here, it says basically anything from VDD to this point, VIH, I'll consider it as the input high. Anything from this point, VIL to 0, I'll consider it as a low, okay? So if you're guaranteed that your output is always going to be in this region, and you're guaranteed that this inverter is going to consider this as the till this point it'll consider it as input high, and anything below this it'll consider as input low, then this whole range you can put all the noise you want and the output will still be low, right? Because this is input high. Same thing here, within this range here you can put all the noise you want, the output will be high, it'll not change, it'll just stick at 0, right? So but by definition, this noise margin, which we call it noise margin low, noise margin high, sorry. Yeah, I think this is how it is defined. So the noise margin high is defined as the input which will swing from VOH and output which will swing from OH all the way to this point VIH, and this inverter will not change its output or will not change it to the point where it'll not affect the rest of the circuitry. It'll still be considered as a low. Okay, so in other words, you are interested in this range, and that's called the noise margin. It's the margin you have for noise to be superimposed on the output of this inverter, and this guy will still not budge and he'll say, my output is still low, I don't care. My input still looks like high, I don't care. So by definition, it is basically VOH minus VIH, right? Now, it may so happen that you designed something that this turns out to be a negative number, which means that this logic has a problem. So you want to make sure your VOH is always higher than VIH. Similarly, when our output is low, you can start injecting noise all the way to VIL for the second inverter, and this one will still not budge. It'll just still remain as it is, and that's your margin. So this is the margin above what you consider as your low. So when your output has settled to low, you can put so much noise here. That's your margin, and the definition is obviously VIL minus VOH. Again, this has to be a positive number. If it is negative, then you have a problem with your gate implementation. Okay, so that's your definition of your noise margins. Maybe I'll just stop here, take a quick question if anyone has question on the noise margins. Anyone has a question? Okay, now I'll come to how we came about to with this definition, the DVR, because it's actually, honestly speaking, it's an arbitrary definition, but it's a very reasonable definition. Why we stop at the point where this derivative becomes -1. Yeah, Subham.
Sir, if any
Yeah,
case my voltage is in the transition region,
yeah.
how will be interpreted?
No, it'll be interpreted as whatever is the logic it is supposed to, right? So for example, this output is high, right? And you put a huge glitch here. at the output, just like what I explained here. You put a huge glitch here. Uh, the input is still considered as a high and the output will remain low. Well, output will
Sir,
also glitch. Yeah.
if I'll come below noise margin,
Then it is unknown. You can't go there. It's unknown.
so
That's
there
your
will be no
definition.
output or some.
There will be output, but you cannot consider it as a high or a low. So you're not supposed to go there. If you go there, then you cannot guarantee your circuit functionality.
Okay.
Okay, so that's not a logic signal anymore. It's a signal. Yeah, of course, if you come, if you're in this region, it's still a signal. You go below this, the output will be some value, but you cannot guarantee operation anymore. This is to guarantee that whatever you are designing, let's say you're designing a ALU, the ALU still will function as ALU, or you're designing a counter, your counter will still function as a counter. You go below that, all bets are off. You don't know. You can't be here. So this is your forbidden zone, basically, as far as digital is concerned. But in analog, actually, we use this. We actually create amplifier. High-speed amplifiers are actually created in this region, just for information. But for digital, there's no. Okay. Yeah, Chirag, go ahead. What's your question?
So, is there any relation between the noise margin NMH and NML? Like in the design, something like NMH should be greater or NML should be greater.
Well, there are certain constraints, right? I mean, it's obvious from here. For example, your NMH plus NML, right, cannot be greater than VDD. So they have to be within the supply, right? That's your uh, one constraint, but usually it is much less than that. So that is probably the only constraint. But when you design gates, they are related in the sense that when you modify this automatically gets modified because the way they're coupled. So they are coupled. In an inverter design, they're coupled. So you change the PMOS to change NMH, obviously your NML also gets affected by it. Okay. I don't know if that was the question or you're asking
Yes, sir,
something
yes,
else.
sir.
Okay.
No.
Yeah, so they are coupled. So in any design, they're coupled in the sense that you cannot independently change NMH and keep the NML same. They will always change by certain amount. You can minimize it, but you can't like keep one independent and have the other one not independent. Yeah, Satabdi, I think you raised your hand. So you had a
Yes,
question?
sir.
Yeah,
Sir, in the VTC, we are observing that it is decreasing. Means there are 2 points VIH and VIL. So at
right,
between that point, the the V out is decreasing. So
right,
in between that transition region,
right.
how we will consider the noise margin, because if we are having this VIH and VIL region, so in between that there will be a transition region, so we can't interpret what will be the V out.
Yes, that's correct. But you're not defining the noise margin in this region, right? Uh, let me just, you're not defining anything in this region. All your definitions are in this region and this region, right? So this is, as far as digital logic is concerned, this is a wastage of your voltage. You're not using it. I don't know if I got your question. Was that your question or?
Yes, sir. Yes.
Okay. Yeah, Prachita, you have a question?
Yes, sir. Sir, so in the case of a glitch, you said that the voltage goes down from VDD to some low value and again it goes up.
Right.
So then how does it happen?
Oh, how does it happen? Well, the example I gave you, I can just repeat that example. So you have a clock signal, right? So this is V0 to VDD, let's say, right? And let's say that it has some transition time. So so dV out over dV in is some value, K, let's say. So now let's say from this point, whatever this node is, you have a capacitor divider, right? And this is your output of that second inverter. So let's say this is C1, this is C2, right? So this current, when so what's the current through this during this period? Prajita, you can probably answer. What is the current?
So minus C1 dV by dt.
Yeah, but dV by dt is 0. So what's the current?
0, sir.
The current is 0, right? So let's say this is the blue one.
Yeah.
Blue one is current, right? Now this slope is some k times. So C times dV out dt will be this slope here, right? That's
Yes, sir.
current. I is equal to C1 times K. And K is, I'm saying, this is a constant ramp, right? You got it, right?
Yes, sir.
And then that current will go into the C2. So the voltage here, if I just plot the current, it will increase to this K times C1 here, and it'll remain constant throughout the transition period. And then the transition period, again, it is 0. Then it'll go back up again, right? And if you look at the voltage, obviously this will be the integration of this voltage, which will actually, because your current is being integrated. So the voltage, let me draw it here, another color. So if you look at the voltage, so let's call this Vx. So if I look at Vx, Vx is sitting at some value, what did we say, VDD, and then it'll start decreasing, and then it'll ramp up, and then, so that's the glitch. This is the glitch. And that glitch happens only around this area, right? It remains quiet, just happens during this area. So if during this area this glitch happens, as long as this glitch is within the noise margin, the uh, output won't exactly be VDD, it'll be lower, but the way the noise margins are defined, and that's what I'm going to explain now, is that your circuit will function fine. There'll be a small glitch, but it'll function fine. Did that make sense,
Yes, sir.
Prachita?
Yes, sir.
Okay. Yeah, you can use as domain or whatever you want, but this is what you're going to get. Basically, we do it. And I just explained to you from a current voltage, finding the current through the capacitor and voltage across it. Okay, so now I'm going to give you the reasoning behind why it is considered as a the dV out over dV in. So this is a inverter characteristics, static inverter characteristics V in out, some inverter, right? So this is V in, V out. So this is V in, and this is your V out. And this is a real inverter. I think this was older technology. It's a 0.6 micron technology. So supply voltage is 5 volts. So VDD is 5 volt, and this is CMOS. So it goes all the way to 0 volt. So it's very small. You can't see it, but this is 0 volt. Okay. And this is 2.5. The second plot here is the derivative of the output plot. So this is like, as it says, dV out over dV in of the plot. Okay. Again, you can't see the plot, so but this is 0. This dotted line here is -1. Sorry. So this is 0, -1. This is -5. This is -9. Goes all the way to like almost close to -20. Okay. And minus is because it's an inverter. So dV out over dV in is a negative number, right? If it was a buffer, then it would be positive number. Okay. So those are the two plots, right? So now let's say your inverter input is, let's take some number. So this is 0.5 here, 1 volt, 1.5, 2 volts. So this VIH number is right here. I mean VIL right here, somewhere around 2.2 volts. So this is 2 volts. Okay. So let's assume the input is sitting at 0.5, and that's because the output OL is 0.5. So it is sitting at 0.5. So if this is sitting at 0.5, you can see that even for 0.5, and by the way, each of these grid you're seeing, they're 100 millivolt, just to give you an perspective. So each is 100 millivolt. So let's say the input is sitting at 0.5 because this inverter output is 0.5. And we add a very small amount of noise. So let's say we add 100 millivolt of noise onto it. So what I mean by that is, so it is sitting at 0.5, and I'm going to add like some noise of size 100 millivolt, peak to peak 100 millivolt to it. So basically, if you look at this input curve here, can't find my cursor here. Input is 0.5. And so what you're doing is you're changing. Let me change this input color. So you're changing this input by 100 millivolt amount, right? So you're going. And you can see that while you're changing this input by this 100 millivolt, if I want to see what the output is changing, the output is absolutely constant. So the output is, this output is just sitting at VDD, nothing, plus 0 volts, right? So you take a small amount of noise, you add it, no change at all. Now let's go to 1 volt. So let's say it's sitting at 1 volt now. So this is 1 volt. You do the same thing now. You add some 100 millivolt noise here. So I add around 100 millivolt noise here. So that's 100 millivolt noise here, which means it's changing from here to here. So the output is again sitting almost flat. Nothing is happening. So, okay, 100 millivolt again, the output is sitting at VDD, VDD, and nothing, almost 0. Okay, let's go to 1.5 volt. So we go to 1.5 volt. So now I'm going to sit at 1.5 volt, and then I add this tiny amount of 100 millivolt noise. Okay, so you're doing the same thing again. You add that. Okay, and now it's going to change a little bit because you can see there is a slope. So you can see this is 100 millivolts. So if I see the output, it's changing about 50 millivolt now. So now the output is VDD minus 50 millivolt now. Okay, now let's go to 2. So let's go to 2 volts here. And then I add that same 100 millivolt here, which means this is the change. And this is still close to 50 millivolts. So 2 volt, I add another 100 millivolt, and the output is VDD, but it changes by another 60 millivolt, let's say. Okay, now let's go to 2.5. So I go to 2.5, add this 100 millivolt, and I'm here right now. So this is 100 millivolt. The output changes by like almost close to 150 millivolts. So I'm at 2.5. I change it by 100 millivolts. The output changes by whatever was the output before. Actually, these are all whatever output I wrote at VDD by 150 millivolt. So which means that whatever noise I applied here, it actually got magnified. Now let's take this point here, which is around 2.7, which is right here. I apply the same small 100 millivolt, the output actually changed by, so 2.7 plus 100 millivolt, then the output changed, whatever is the output, by 1, 2, 3, 4, 5, 500 millivolts, or almost 600 millivolts. So noise got actually amplified. And then I move here, it got reduced. Then I move here. Then when I come here, it's less, less, less. And then, okay. So the idea why it was choose 1 is because it was decided that when I'm putting some noise here, your output should have at least that or less. If you're amplifying noise, that's the reason you don't want to be. Okay, and so obviously, which is that region? That region is the point where dV out is equal, dV out over dV in is equal to -1, because less than here it's 0.9, 0.8. So whatever is your noise, so let's say I had some delta V noise, I multiply it with dV out over dV in, that's going to be my output. That's my delta V out. If this number is less than 1, then this noise will be less than whatever was the input. If it is greater than 1, then it is going to be more. And I don't want that, because if I have a set of inverters, they'll just keep amplifying. And then after 1 or 2 inverters, then the output will be just, completely messed up. So that is the reasoning behind why we choose the slope to be -1. Did this make sense? I'll show just a quick math behind it in the next slide, but this is the principle behind it, why we chose it. So did it make sense? Maybe I'll just stop quickly to see if any of you have a question. Any question? This makes sense, or absolutely no sense, or somewhat made sense, or whatever question you have. Okay, hopefully it makes sense. So I'll show you the math behind it in the next slide. So hopefully that'll kind of clarify it a little bit. So if I take the same series of inverters here, basically what I'm saying is that, so let's take this inverter, for example. Okay, so this inverter, if I write it in a sort of a mathematical formulation, I'll say the input, the function of the out, V out, sorry, let's write V out is some function of V in. It's a nonlinear function. If it is a linear function, I would have written it as a K in times V in, but it's a nonlinear function, right? So basically that's what I'm writing. So output is a some function of V in, and in this case, I know it's a nonlinear function. Okay. Now, if it is a nonlinear function, I can add this small delta noise to this V in. So instead of V in, I said it is V in some delta V noise. And I assume that this is a very small quantity. How small? Uh, Small enough that you can what's called linearize it. Assume that the example I was giving before, I was applying a small one, the output was a bigger version of it. If it is bigger version, a distorted version of it, then I can't use this analysis. But the principle is still the same. So this is just to kind of make your analysis easier. So small enough that I can neglect higher order terms. What I mean by that, I'll come to it in the next year. So you basically say, okay, it's some function. Now instead of V in, I put V in plus delta V noise, and I want to see what is this noisy voltage now. Okay. Now I can, because it's a nonlinear function, I can do a Taylor expansion of this. Okay. Or Maclaurin or whatever you want to do, right? A Taylor expansion of this. Now Taylor expansion of any series is the function at V in, which is called the DC value. This is your DC value. And then whatever is changing, that you have basically some constant times the first derivative, then you have the second derivative, V out over V in times delta V noise, some constant, and then so on. But because our assumption was that this delta V was very small, which means that this derivative is also going to be, I mean, delta V square, because this is delta V square and then delta V cube and so on, we can actually neglect all the higher terms and just take the linear term, which is basically saying that we have linearized this function. Okay, now it's clear from this function because now your output is what you desired, right? You desire, this is your desired value because that was your definition, that my output is some function of the input. So that's your desired input. This is your undesired output, which is some some gain term, some constant, which is the derivative of this time times the delta V noise, right? And like as I was explaining in this slide before, so V out is equal to this modified V out is the function of V in, and then plus sometimes V noise, right? And you want this term to be less than 1 or minus 1 in this, in our case, because if it is more than greater than 1, then this quantity would be larger than your input delta V noise, and you don't want that. You want to keep it at least that amount or less. And so that's the principle behind why we chose this as this number as -1. So if I go back to the curves, the derivative curves here. So that's where you said, okay, this derivative 0, 0, 0, 0 starts 0.1, 0.2, 0.3, 0.9 minus 1. Okay, you stop here and you say, okay, this is my margin. That means this whole range, the input to this gate will be considered as a low and the output will not change much and it will not magnify the noise. In this range, you forget it, and same thing at the output here. You say, okay, this input, the output is still low, and you keep decreasing it till this point where the gain starts increasing, and you say, okay, I'll just stop here, and that's your noise margin high. Okay, so so that's your sort of both your graphical and mathematical way of describing why you're choosing that derivative to be -1 to define your VIH and VIL. Any questions on this so far? And hopefully everyone is clear about what the noise margin is right now. Or if you have any questions, please ask right now. Okay, looks like. Okay, so now that we have the definition, so we'll take few gates and do some analysis. And in when you're doing static inverter characteristics, is essentially we are just doing noise margin power calculation most of the time, static power calculation, not the dynamic power. So the power which is involved for charging and discharging the cap, you don't do that with static analysis. You just do what's called static power, and explain a little bit after. I won't go much deeper into it, but I'll just explain it to you. Okay, so if you look at the resistively loaded NMOS inverter, so here the load is actually a resistor. So I think I've already sort of gone through that in the first slide, but quickly go through it. So the way this works obviously is when your input is 0 or less than the voltage, which this doesn't have any channel, this one is off. So usually there's a load capacitor here. So in VLSI, typically there's always a cap here, which is routing plus its own cap plus the gate cap or whatever cap is in the next gate, right? So you have this um, capacitor which is being charged. So obviously after some time, 5 times tau or anything, this will charge to VOH. In this case, it will charge all the way to VDD because there's no current when this is off, right? So that's your output. And when I switch this on, so I make this input to VDD, this one turns really hard on, and which means that this resistance is very small compared to this resistance. So this will charge to a level where this is a voltage divided ratio of these two resistors over here. Okay, so that's your normal functionality. And if I so I just explained it here that V in less than VT0 and NMOS is off, output is VO, V out is equals to VDD. If V in is equal to VDD, then the NMOS is in the linear region, because this output, if you have designed it well, the way you're designing it, you want to make this voltage really, really low. So in that case, this will be in the linear region because this input is VDD and this is VOL, which is very close to 0. So that means this is in the linear region, right? So because in the case of output VOH, the output just goes to VDD, right? But now it doesn't go to ground. So what's the value? Well, you can just model this as two resistor dividers, right? So this is, let's call this RL, and let's call this RN. And if you remember, when we did our IV characteristics, we said there are two regions, right? Linear region and saturation region. But in the linear region, I also derived the approximation where I said if the VDS is very small, then the IDS can be written as what? Mu n Cox W over L VGS minus VT0 times VDS, right? Because all the square terms you can say I neglected. So if it is 100 millivolts, for example, 0.1, square of that is 0.01, which is 10 millivolt. You can say, I'll neglect it. There won't be that huge. So in this particular case, this will be mu n Cox W over L VDD minus VT0, and VDS is nothing V out, which is that quantity VOL, right? So that's your IDS flowing through this. So this is nothing but 1 by Rn, this quantity here, because IDS is equal to VOL by R. So that's 1 over Rn, right? So or Rn is equal to 1 over mu n Cox W over L VDD minus VT0. Okay. And that's it. So your output low now is just a resistor divider of it. So VOL is nothing but Rn times Rn plus RL times VDD, right? So obviously, if you want the VOL to be really, really small or close to 0, then you want this quantity Rn to be really, really small, right? I mean, yeah, really small compared to the RL, so that it's almost equal to 0, the ground. So in other words, it's a short. So if I take a quick example, so let's take what is it, mu n Cox, let's say it's like 600 microamp per volt square. I'll just put the whole thing, W over L times mu n Cox is this thing. And let's say VDD is 1.2 volts. VT0 is, let's say 0.6 volts. What else is there? Okay, so if that's the case, then you can calculate the Rn to be 1 over 600 microamp per volt square times VD minus VT, which is times 0.6. So you can say this is 10 to the power 3 divided by 0.6 square, which is, let me just quickly calculate here. How much is it? So 0.6 square. So 2.77 kilo ohms, right? So so now let's take the load, let's say to be 20 kilo ohms. And so Rn, I'm just going to approximate to 3 kilo ohms. So VOL is equal to 3 times 23 times VD, which is 1.2 volts, which is 1.2 times 3 divided by 23 equals to 0.15, approximately 0.15 volts. Okay. So that's your output load. So your output doesn't go all the way to 0.15, I mean to 0 volt, because you have a load which is constantly on. Okay, so that's sort of a quick way to calculate it. Obviously, if you want to be really, really accurate, then you use the entire equation of the linear equation with the VDD square, and it'll change by a few percentage, because since your output you have calculated to 0.15, your assumption that VDS is small still holds, right? Because 0.1 square is like 0.01 something or 0.02 something. Okay. All right, so we calculated VOH, which was VDD. We calculated VOL, just the resistor divider. We used the resistor divider principle to do it. VIH, so what I'm going to do is I'm going to show you a quick way how to just the principle behind how to calculate the other two factors, which is for the noise margin, I also need the VIL and VIH, right? So for the inverter, so let's calculate VIL. So what's the definition of VIL? The VIL definition is when the output is high and starts rolling off, the input voltage at which dV out over dV in equals to -1. That's where you want to define that voltage as Vn. So let's first see. So it's a resistively loaded this thing. So your input is VIL, obviously. Vin is VIL. This is RL, and output is still very high. So the NMOS is in what region? Saturation, right? So NMOS is in saturation, right? So if I write the NMOS current equation, so it is mu n, if I write the current equation, it's mu n Cox over 2 W over L, then VGS minus VT 0 square, and VGS is nothing but V in, that's the input voltage, minus VT 0 whole square. And forget the lambda term, it's not going to change your calculation by much. So we'll just, to keep it simple, we'll not include the channel and modulation. So that's your current through the MOS transistor. So that's your IDS, which has to be the same as IRL, right? And IRL is nothing but, so this is your V out. You don't know what it is, so it's going to be VDD minus V out over RL, right? So you want to take the derivative from both sides. So if you take the derivative from both sides, so D over dV in on both sides, because you want the quantity dV out over dV in, right? So if you take the derivative on both sides, so left one will become mu n Cox W over L by 2. Then take 2 times of that, so they'll cancel. And V n equals to 0. Yeah, so that's it, right? And then this one is minus dV out over dV in over RL, right? So, and sorry, I still need this term here. So V in minus VT0 equals to that term. So if I substitute this quantity to be -1, then it's mu n Cox V in minus, well, I can now say, because I've substituted dV out over equals to dV out over dV in as -1, this input by definition is now VIL is equal to 1 over RL, right? So if I expand the whole thing, then VIL is equal to VT0 plus 1 over mu n Cox RL. So at least to the first order, it makes sense because you don't move at all. The output doesn't move at all till like VT0. And then this is the term, which is 1 over mu n Cox RL, which we just calculated. Okay. So depending on your resistor value and your mobility of the transistor, this quantity will be decided. So obviously you want this quantity to be large, which means you want this product to be small. Okay. Or in other words, what you want is you want the NMOS to hold on as long as possible. You want this, if I show you, once, just can't see the cursor. Sorry. Oh, sorry about that. I don't know why it erased it, but okay. So yeah, you want ideally to hold off as if you want to make the noise margin low as possible. Sorry, I don't know why it got erased. You should have that in the video, but I'll just write the expression. VIL was VT0, like I said, till VT0, obviously nothing moves. So that you get it for guaranteed, and then divide mu n Cox RL. Oh, actually mu n Cox W over L RL. I missed that term there. Okay, so that's your VIL. So that's how you calculate the input low voltage, VIL. VIH is also the same principle here. So in this region of operation, I mean, in this region, your, what do you call it?
Linear.
Yeah, the transistor is in linear region. Thanks. So in the linear region, you can write the entire equation, but you can just write mu n Cox W over L VGS minus VT times V out. You can use this equation just to approximate it. And that should be equal to also VD minus V out over RL, right? So this will be a little complicated because you'll see that when you take the derivative, you'll still get a V out term because now you got, times V out. This is, let me just erase this. So this is V in. So again, you take the derivative of both sides, dV over dV in of this. And so this will equal to minus, just like before, dV out over dV in over RL. And then substitute dV out over dV in equals to -1. Solve it, and you'll see in this what will happen is you'll still get V out term. So you put that V out here, and retract it back. It's textbook. If you have any doubts, you can always refer to the textbook. But I'm just showing you how, in principle, you calculate it. Okay. Any questions so far on how we calculated the 4 noise margin terms? Basically, VOH, VIH, VIL, and VOL. Any questions so far? No questions. Okay. All right. So I just will quickly show you what the power. So this in digital logic, usually the powers are divided in two categories, what's called the static power and the dynamic power, right? So static power is to do with all the power which is consumed, even if you didn't have any capacitance in your system at all. Okay. So that's consumed anyways. And the dynamic power is the power consumed to charge and discharge a capacitor. Okay. And you add that up, that's your total power. So since we're doing static characteristics, I'm just going to show you the static power part of it. Okay. So for example, in this case of a resistively loaded NMOS inverter, your power from and the power consumed from the battery, which is VDD here, for example, is whatever is this IDC flowing through this times the power times the voltage supply, right? So VDD times IDC. Now, because it is signal dependent, right? Because when the input is low, then no power is consumed, right? Because this one just charges it up. The output goes to VDD. The current through the resistor is 0. No power is consumed. But when Vin is let me write that down. So when Vin is equal to 0, IDC is equal to 0, right? When Vin is equal to VDD, what's IDC? IDC is VDD divided by RL plus RN, right? So for example, if you take the last case where let's say the output supply voltage is 1.2 volt and we calculated this to be, what is it, 22 kilo ohms, 23?
23.
Yeah, 23. So just for easy calculation, I'll do 24K, right? So 24K means 1.2 by 2.4K would have been half milliamp. So it's half of that. So 250 microamps is what you get, right? So the power would be the power DC when Vin is equal to VDD is equal to 250 microamps times 1.2 volt, which is approximately 240 to 50, approximately 300 microwatts, which is huge. Like entire digital chip now consumes 300 microwatt. So for a gate to be consuming 300 microwatt, that's a lot. And this is when Vin is equal to 0. So the way the static gate calculation is done is because, so let's say, for example, the input was just a clock, right? Or some data, which is going 0, 1, 0, 1. So if you look at the IDC, it was 0, it'll go to 250 microamps, 0, 250 microamps, 0, 250 microamps, 0. If I take the average value of this, it'll be 125 microamps. And that's the average power which is dissipated, which is roughly, what is it? Something like 150 microwatts. Okay, and that's what this equation is. It's basically saying that find the power when the input is high, find the power when it is low, times VDD by 2 is the average power which will be consumed. But obviously it depends on the thing. So that's your static power consumed. So this is not taking into account any capacitor, right? So because if you have a capacitive load now, so for example, if you have this capacitive load now, then every time you charge this, then you consume half CL VDD square. Discharge it, you consume this much. So CL VDD square is your power consumed for a total cycle. Okay, so that's all I want to talk about power. It's just that you know that it's a power which is consumed, what's called the static power, even without any capacitive load. Okay. Oh, I just wanted to show you this. Sorry. Okay, so here I have an example. I think this is an example from the book or probably from the book. So what I've shown here is, so in this example, VDD is given, some mu and Cox, W over L is given, VT is given, and it is asked to design that resistive loaded inverter, the one on the top, with a VOL of 80 millivolts, right? So you can see that you can achieve that by different combination, because it's not a constraint condition. It depends on, 1 second. Sorry. Yeah. So you can see if you take the W over L ratio as 1, just can't seem to find. Yeah, if you take W over L as 1, then your resistive load is 263 kilo ohms, right? And then your consumed power is only 2.56 microwatt.
So,
And yeah,
Sir, I can't
The
see the
screen
screen.
sir,
is
you
not.
can see it.
yes, sir.
No, sir.
No, can see.
You can't see anything or just the table.
Sir,
Sir,
not
anything.
anything.
So the screen.
So your
Sorry.
slide is not visible.
Oh,
So your
that's
slides
weird.
are not visible.
Yeah, I'm fixing it. Just give me a second. For some reason, the sharing stopped. I must have. Okay, can see now?
Yes,
Yes,
sir.
sir.
Sure. Yes, sir.
Okay, sorry about that. Somehow, I don't know why the sharing stopped. Okay, so basically what I was showing was, this is an example where for the above inverter, resistive loaded inverter, the VDD is 1.2 volt. This is the Kn value given. This is the VT 0 value. This is what you're supposed to find the value of RL and W over L for a VOL of 80 millivolts, 0.08 volts. Okay, but there is no one value of RL and W over L. Okay, for a given W over L, there is a RL value. So you can see for W over 1, W over L of 1 and resistor value of 263K, your output consumed power is 256 microwatt and your output VOL is 80 millivolt. If you calculate, you should get it. I haven't cross-checked it, but I'm having faith in whoever did the calculation. If you do 2, then obviously this drops by half RL because you want same VOL. So your output now increases to 5.11 because it's VDD by RL plus RN. If you choose W over RL is 3, then it drops to 87 and the total power consumed increases even more. And as you can see, when you get to RL of 43, RL is 6, W over of 6, then the power went from 2 microwatt to 16 or roughly 2.5 to 15, sorry. So which is roughly 3 times 6 times more power, but it is the same VOL and same VIL and VOH also, because if you calculate it, you would probably see that they are also the same, almost the same. Okay, everyone hopefully understands this. So my question would
Sir,
be, yeah, go ahead.
sir, here my load resistor is 263, so it is larger. So here I am getting less power, but
Yep.
W by L ratio is 1. So when the resistor value is larger, we will be consuming more area. So how W by L will be? Here W by L ratio is less.
So what is your question?
Sir, I was asking here W by L ratio is 1. That means it is less as compared to all the values we are taking. And here resistor value is larger. So we
Right,
will be consuming more area as resistor is
correct,
large.
right. So your question
So,
is which one do we choose, or so yeah, so I was just about to come to that. Like, so what is the difference between all this? Is that which one would you choose? And that's where I was coming to. Is are you asking like which one do you choose because this register value is larger?
yes, sir.
Okay, and so it's a area power trade-off, but there's another trade-off also. So it's a area power trade-off, right? Power trade-off for this particular design. So, typically a resistor, for example, if I'm doing a poly resistor, it's some so this is how your resistor is going to look like, right? So it's some row sheet times, sorry, 1 second. So this R is, RL is equal to some row sheet or row poly times L over W, right? So W is usually you keep it to whatever minimum and you keep increasing the L. So in other words, W times L, the area is larger for this. So let's say this is some area A1. This will be roughly A by 2. This will be roughly area by 8324 A by 3. This is roughly A by 4. This is, and so on. So you get the idea. But the transistor size is increasing. So let's say this is a transistor. So this is obviously 2 times 80. This is 3 times 80. This is 4 times 80 and so on. So this is decreasing, but this is increasing. So when you add the total area MOS plus the area of resistor, that's your total area total, it's actually still decreasing because this is usually your significant part of the area when you're doing a design like this. Okay, so even though this is increasing slightly, the total area is still decreasing, but your power is increasing. So that's the trade-off. So your question was, um, uh, how do we choose? Well, it depends on your application. If your application is absolutely power sensitive, you're doing an IoT sensor node, for example, and you want to run the entire IoT sensor, just give me a second here. Yeah, so you're designing an IoT sensor node, and your entire IoT sensor node is supposed to run on a coin battery cell for 5. There, you're ready to spend more area to consume as less power as possible. Whereas you want to do a high-speed design, let's say you're designing a high-speed computer, then you don't care about the power there. You just want to have a minimized area because your circuit is so huge. And there's another term which is not here, which is the speed. As you decrease the load resistance RL, because the speed is decided by your rise time is decided by RLCL, and your fall time is by RNCL. So you can see here tau is going to be, so let's say this was tau, this will almost become 2 tau, sorry, speed increases, so the other way around. So we start here tau. So this will become almost 2 tau, 3 tau here, 4 tau. So your speed is decreasing as you go higher in this branch. So there is a speed aspect to it as well. So it's really not area power, but it's area power and speed trade-off. So any design when you do this, these are always the trade-off you're doing, and it always depends on the application you're working on. There's no one single answer for it. It depends on your application, and sometimes your application is such that you're not meeting your requirement. You want the lowest power but with less area, and that's when you want to look at a different device or a different technology, different foundry house and so on. So for a given technology, these are the available. So there will be available sheet row, different types of sheet rows, different types of NMOSs, different types of PMOSs. With that, and given your application constraint, you have to just design your circuit. Okay, and that's where creative designers come into picture, because then you say, oh, I can do this in circuit, I don't have to depend on this. I can do switching here, I can do dynamic here, or whatever it is. So that's where circuit design comes in. So you do all your innovation in circuit design, because the technology, it's kind of fixed, you can't change it. Did that answer your question,
Yes,
Sadabhi?
sir. Yes, sir.
Okay.
One small doubt.
Yeah,
Yes, sir.
go ahead, what's your doubt?
Sir, resistor is rho L by A, and W.
Rho
Here,
L by
the
W, yeah,
resistor. Yes, sir.
so
So
yeah,
the resistor and NMOS are both in series.
right.
So my length W by L means L1 plus L2. Both the lengths will be added. That means it will
No,
be
no, no,
get
no.
doubled if both have the same length. So my resistor value should be increased because it is L by W.
No. So you're confusing between two stuff. So this is not a resistor. This is actually a physical resistor. So in other words, let me see if I can find a blank screen. Yeah, if I draw the layout, 1 second, let me just bring up a. Okay, so this is actually a physical resistor. So if I just draw the layout of this, so all you have is a resistor, and if it is a poly, it's a long resistor, let's say. And then on one side, you connect it with VDD. So this is going to be your VDD rail. And then you have the transistor, which is so you'll have your diffusion, and you'll have your gate, and then the connection would be, so you're going to make one connection here and put a via, so that's metal 1, let's say, and that's your drain of your NMOS. So this is your metal for V out, and then you're going to get a gate connection. You're going to do it through another metal, let's say. That's your gate, which is V in, and then this is, like as I said, VDD, and then you're going to make another connection for your ground. So that's your ground rail. Okay, so that's your AC. Now this one, so let me call this LR. So this one is the length of the resistor, and this is the WR. So your total R value is row sheet times LR over WR. And this one obviously is the length of the transistor, and this is your W. That's W rail. Okay, so they're two separate devices. You're not, but obviously they have the similar response. You increase the rel L for this one, your resistance will vary. Okay. Obviously you increase this length, but you never increase the MOS length because you want the MOS to be as um, small as possible. So Sadali, did I answer your question?
Yes, sir. Yes, sir.
Okay. Any other question?
Sir,
Yeah.
sir, the load resistor also depends on the technology of which it is used to fabricate.
Yes, it does. So good question. So
So how?
yeah, so there are different types of resistors. So I can give you some examples. Like for example, in a particular technology, they might have what's called a N plus poly, which is actually what's your gate is in. So this one, usually the sheet row will vary, right? This what's called a salicylated and a non-salicylated one. Salicylated and non-salicylated one. Salicylated. I'll explain a little bit what is salicylated and non-salicylated. So they'll vary anywhere from 300 or 200 to 1000 ohm per square, which, okay, so you take 1 square, that much how much you're going to get. Then there are N-well or diffusion, so ND or N-well resistors, and these can be as low as like 10 to 50 ohms or even as high as 1K ohms. The N-wells are around 1K ohms for per square. So typically these are the resistor. Obviously metal you can use as a resistor, but metal is very, so if you take metal, for example, metal 1 or 2, they will be typically like zero point 0.1 or 0.01 ohms per square, right? Obviously you want them to be as small as possible. So these are all the resistors you can use in a technology. But like I said, every technology has varied. Some technologies will allow you to what's called a high raise. high res value, high resistance. They can be all the way up to like 6 to 10 kilo ohms per square. So yeah, so the salicylate I'm talking about is, so what happens is, it comes because the way the NMOS or the PMOS is fabricated. If you remember the self-aligned gate, right? So you put the poly on top of it. After the poly is laid, you remember we do the, yeah, I drew the N plus first, but after that, you do the ion bombardment, right? So you do the ion implant. Remember you did your VT calculation with DI. So that's the DI. So wherever the gate is, the ion doesn't get implanted. That's the purpose for the gate. It acts like a mask actually, but the gate itself gets bombarded, which we want because we want this to be as less resistive as possible. So when they do this and annihilate, this actually becomes, the gate looks like a resistor, and this is typically, but this is usually very resistive. So this can be as high as 1 kilo ohm per square. So for gate, they do what's called a salicide. They actually do a titanium, like a thin titanium kind of a implant on top of it, another thin layer on top of the poly, and this is called salicide. Okay, and this will drop the resistance to like, even 100 ohms per square. So when you want a low res, you do it like as if it was a gate. If you want higher value, then you actually stop the salicide. You say, wherever you want to do the resistor, you said you stop the salicide mass, they'll stop it. If you want even higher, you say, well, don't anneal this. I mean, don't just keep it fractured. So keep it almost like a polycrystalline, which is harder to do because the melting is done all the sides. So they have processing techniques. Actually, I'm not sure how they exactly do, but you can do as if it is almost polycrystalline in nature. Okay, so Prajita, did that answer your question?
Yes, sir. Also, sir, with technology and RL, is there any like area type of relationship between them? Like if RL is larger, so the technology has to be like we have to do it in a larger technology or something. Like factor is coming in between.
So I'm not sure if I understand the question. So you're asking, is there a relationship between the type of resistor and the technology?
I'm asking, sir, RL depends on the technology. In terms of area, is it possible?
Sorry, you just broke off. In terms of area, is it what?
Is it possible, like for lower nanometer technology, the RL
Yeah.
should be lower value, or like in terms of area, if we judge also, it should depend,
Oh,
no?
I see. I see what you're saying. Okay. So your question is like, for example, when we go from, I think this is what you're saying. So let's say we go from 0.18 micron technology, which is, let me write in nanometer. So 118 nanometer technology, we go to, for example, a 28 nanometer technology. So you're saying like, for example, your transistor, your NMOS size decreased, right? So the area is went from big to small. Is there a relationship between for the resistor from going from here to here? Does it get smaller for the same value, you mean? Is that what you're asking?
Yes, sir.
Yeah, so short answer is no, in the sense that, see, the scaling in a typical technology is purely done from a transistor perspective. So it's purely from the MOS perspective, the scaling is done. Resistor is actually just so happens whatever is the gate, right? So, and so for example, the gate width can be allowed to be as small as, for example, 0.18. But in a resistor, they will not allow for that small range. They will say, no, no, you have to keep it 1 micron because you're doing long resistors and we can't guarantee it. So the short answer is actually the resistors don't scale that much. But yeah, there are some effect. So the resistors and capacitors are actually almost, especially when you're using a digital technology, they're almost a parasitic effect.
Yes,
Yeah,
sir.
sorry, parasitic effect of it. So you're getting as a result of building a mass. Um, So it's whatever you get. But obviously, when people start using it for analog, they will usually tell the process guys, hey, we want a high res value or a low res value. Can you do this? Can you do that? So they'll add some mass at a higher cost. And those who are doing some analog high performance tests, they'll say, okay, I'll choose this mass and pay you a little bit more. Like somebody who's doing RF design, they might want a certain type of mask on their resistors and yet to make it high speed. So the process guys will add that mask, but it'll be an extra cost, which the digital guys don't want to pay because they want minimum cost and they don't need those devices mostly. They just want a fast NMOS and CMOS, that's all. And metal layers. So for them, the optimization is slightly different than the optimization for um, the digital guys. Okay, makes sense? Okay. All right, so that brings us to CMOS now. Now, like as I said, in the loaded one, in the MOS, the biggest problem people faced, and that was really one of the major reasons of the birth of CMOS, is the static power. So the static power, they wanted to kill it because let's say you're running a circuit at a very low frequency and you want only to spend the power in charging and discharging. You don't want to spend any other power. Whereas in the resistive loaded one, like the one before, you're basically just drawing current half the cycle. So that's not desirable. So that's where CMOS came to picture. And the CMOS, the idea is very simple, obviously. So you have the complementary switches. So you have a switch which turns on when the V in is, let's say, high. But during that time, the PMOS switches off. And when this switches off, when the input is low, then PMOS switches on. So that way, only one switch is on to charge or discharge this load capacitor here. Okay. And in this circuit, obviously, if you look at, because we'll be writing some equations, so I'm just going to um, um, give some definitions for it. So the VGS for the end device is obviously whatever is the input voltage, Vin, right? And the VGSP for the PMOS is Vin minus VDD, or if you want to take the magnitude of it, is VD minus Vin. And the output, the VDS for the PMOS is V out minus VDD. So because V out is the drain here for the PMOS and that's the source, so that's your VDS. For the NMOS, it's V out because it's V out minus 0 because that's your ground, so that's your V out. And in case of a CMOS, obviously because only one switch is on, your VOH is the supply voltage and VOL is your ground voltage, because when this is on, it'll just discharge it completely to ground basically. Okay. So that's the definition of it. And this is, I'm just showing you that's a transfer curve again. So basically when the input voltage is 0, you start with output voltage at VDD, then this remains like that till your input voltage is VTN. Once it goes above VTN, the NMOS turns on. And so obviously the NMOS is in saturation, the PMOS is in linear, and there's a middle region where both in saturation. I'll show a diagram with a little bit more detail in it. And then, you know, the opposite happens where your input is high enough right now that the NMOS turns on, VDS is low enough that it is in linear region right now, PMOS, and then once this becomes VDD minus the mod of VTP, the PMOS switches off and then the NMOS is completely on and the output is equal to 0. And this is that gain curve I showed you just a while ago, defining the VDD and VIH. Okay. All right. So I'll just quickly show you the regions of operations when you're going through this. So this is it. That guys, just give me a minute. I'm just dying here. So Okay, I'm back. Sorry. So, so in case of the CMOS inverter, like we saw, so this is your input voltage, V in obviously. This is your V out. And obviously when input is 0, because only the PMOS is on, so this charges up all the way to VDD, right? And in the opposite case, the NMOS completely discharges to the 0 volt. So VOL and VOL is 0 and VOH is VDD. So VOH is equal to VDD and VOL equals to 0 volt. And this remains the case till your input crosses till VTN, right? Till VTN, obviously you have a little bit of subthreshold current. It slowly starts charging a little bit, but you can assume that, okay, just give me a second here. Sorry, okay, I'm back again. All right, so till the input is VT, uh, the input MOS remains off, the output charges to VDD. And so this is, so let's call this region A. So in A, basically this NMOS is cut off and PMOS is obviously in kind of linear region. I mean, just charging, it's sort of off also. So same thing happens for, this is, you can call this VDD minus mod VTP. From here till here, the PMOS is off, the NMOS is completely on. And so obviously the NMOS is in linear, PMOS is in cutoff. So the PMOS is cut off in these regions. Okay. And if I draw a line, so let's call this line VN minus VTN, right? So if I draw a line here, and this blue rectangle you're seeing throughout this entire region, when the output is in this region, blue region, then the NMOS is in saturation, right? That's because the gate of the NMOS is Vn. So if your drain is Vn minus Vtn, that means VDS is equal to VGS minus Vtn. So it always remains in saturation, right? So that's the blue region. Now, if I draw a similar line here, and this line is VDD plus VTP, or you can say VDD minus of mod of VTP. If you draw this line, then in this square over here, the PMOS is in saturation because for the same region, because your drain voltage VDS is always greater than VGS minus VT in that situation. So obviously you can see now that in this region of operation, let's call this B. So NMOS is in saturation, PMOS is in linear. And in this here, both of them are in saturation. And in this case, PMOS is in saturation, NMOS is in linear. And in the case of E, NMOS is in linear and PMOS is cut off, right? And then you can define the same kind of definition if you take this slope here, dV out over dV in, and that gets defined as your VI L, that's your low. And if you do the same definition over here, dV out equals to -1, then this becomes your minimum voltage for which the input is considered high, or VIH. And so obviously that's your noise margin high, and this is your noise margin low. So I've just tabulated this in the table region here. So in this region A, like I said, your NMOS is cut off, PMOS is in linear. Then once it goes higher than VT but less than VIL, or within the VIL region, your NMOS goes in saturation, PMOS is in linear. And then during the mid region, both of them are in saturation, and then it reverses. NMOS goes into linear, this goes in saturation, and finally PMOS cuts off when the VGS is less than VT. Okay. So so when you're doing all your calculations, depending on which one of these regions you are, you write the appropriate IDS equation to solve all your static static equations. Okay. Any questions on this so far on the regions of operation? Any doubt here? Okay, so looks like hopefully it is clear. Okay. All right, so I wanted to just show this. So the static power, like obviously we chose the CMOS because we didn't want to consume static power. That's true. Like for example, we had shown the resistive loaded one, right? For the resistive loaded one, if this was your input, high, low, during the high phase, your current went from 0 to some value when the input was high, and then that was the case, right? So, and this is the part we didn't want. This is the IDC we didn't want, right? And with the CMOS case, that's true now. So with CMOS, sorry, CMOS case, if you look at the current, so CMOS, let's say, so it stays 0. But during this transition, because these are finite transitions here, you will actually get static power, but it's only at the edges, right? And the reason for that is once we cross the VTN, both of them are on. So you're going to have a power from VDD. So let's consider this CMOS here. So once this VN is greater than VTN, this is on, this is on. So you're going to consume power. So you're going to consume, but it's very little power because your PMOS is a high value resistor here right now. And then as soon as you keep going up and both of them are in saturation right at VTH, you have the maximum current flowing through this device, which depends on the W over L ratios. Unlike in the case of resistive loaded, it was VDD by RL plus RN. Here, it will be whatever is your saturation currents over here. Okay, the same with resistive loaded RL2. It's just that the RL is just a linear resistor. And then as you transit slowly to the 0 volt input high, then obviously it starts going down. So that's your static power consumption basically over here. So in case of a CMOS, it really depends on your switching frequency, because if your switching frequency is really higher, so you're going to get these spikes, really high. And then when you take the average, it'll be almost equal to, let's say this peak was 100 microamp, the peak will be almost 100 microamp. But if it is a low frequency one, then you're going to get this peak. The next one is going to be after a long time. And then if you take the average, obviously this average is going to be much lower, right? Whereas in case of a static one, actually in case of low or high, it's always, if it is a 50% duty cycle, let's say, it's always the same. Okay. Any questions on this slide here? Okay. So bunch of equations, but I think because I've explained you the principle, I'll not go into the detail of it. So in case of a CMOS, like I said, VOH and VOL calculation is pretty straightforward. VIL and VIH, it's the same principle, right? So basically you're calculating, for example, VIL in this region here, right? So for VIL calculation would be this region here, right? So you would write your IDS NMOS for saturation region, which should be equal to the IDS of PMOS in linear region. So this is for VIL calculation. You have to do that. For VIH calculation, you are in this region. So that's this region here. So in this case, you want to write the IDS NMOS for NMOS in the linear region and IDS PMOS in saturation region. And that will be your VIH calculation. Okay. So, and that's what is happening in all these calculations. So for VIL, you can see that this is your NMOS, right? So this is your NMOS. You calculate your saturation, you write the saturation equation, and because they're in series, the current has to be equal. This is your PMOS in a linear region. And if you want to get a very approximate answer, you can assume that V out is very high or VDS is very small. So you can actually write the linear form for this, where you can kind of neglect this. Okay. If you want a quick calculation, you can do that as well. So same principle, take the derivative, apply dv out over equal to dv in as -1. If you solve it, then your VIL turns out to be this quantity. And as you can see that there is still a V out term here. So you have to take this, substitute back in this equation here, and then solve for V out and substitute back here. Okay. So typically we don't do a whole lot of, this is just to understand where it is coming from. Typically what we do is once we size the transistor, we simulate it, we know how to size them. Okay, like for example, maybe, okay, let me maybe ask you this, right? So let's say, you know, you got a certain VIL, right? And let's assume, so let's say this was a 1.2 volt. So let's say this was 0.3 volts is what you got, okay? Now, if I want to increase it, which transistor size should I increase, the NMOS or the PMOS? Anyone?
PMOS.
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 Okay. And
PMOS.
why PMOS? Any intuitive answer?
So, sir, if we increase the strength of PMOS, it will hold for a less, for more time,
Yeah,
for
exactly.
more value.
Right. So basically, what you're trying to do is you're trying to shift the curve like this to the right? Which means that this is the PMOS. So the PMOS is going to fight the NMOS for a longer time before if you want to switch it on. So that's why you want to make the PMOS size larger to make this. So typically in a simulation, I mean, when you're designing it, you get to a certain VIL and then you say, oh, I want to increase this. Then you just go and increase this size a little bit and say, okay, I got my number, because the calculation you're doing it is very approximate. The other way to look at it is like this VTH point, you want to move it to the right. And in VTH, this is in saturation, this is in saturation as well. So for a same V in, if you want to move this to the right, which means you want a lesser voltage on the VGSP, which means that you want to make the W over L stronger. Okay, so that's the other way of looking at it, how to increase the noise margin lower. Okay, and for VIH, it's the same thing again. You basically take the equation for the NMOS, the linear equation, PMOS for saturation, take the derivative, apply this condition, and you should get the number for VIH as well. And then VTH, because both of them are in saturation, you can apply VT, that is the threshold voltage. Again, this is the threshold voltage of the inverter. It's not the NMOS threshold voltage, okay? All right, so I think that's all I have. Yes, Puneet, go ahead.
So, sir, I have just two things.
Yeah.
So, in NMOS and PMOS, we have this VTN and VTP.
Yeah.
So I want to discuss two scenario. The case one where VTN is 1 volt
Yeah,
and VTP is -1 volt.
correct.
So that's a one
So you're saying VTN is
1 volt,
1 volt and
and for the VTP is -1.
-1. Okay, so this is a symmetry. So actually, everything we have been discussing so far is actually this condition
Yeah.
here. So, okay, and the second condition you're saying,
Second condition is VTN. Let us suppose if I will increase the VTN, then I'll
okay, like
make it.
1.5 volt maybe.
No, so on a higher side, maybe like 2.5 or 3 volt. Let's see the 3 volt,
Okay,
and VTP again -3 volt.
okay, but this is still the symmetry. Just your supply voltage has increased now.
Yeah. So in the
So,
both the case, let us suppose VDD is 5 volt. I'm just talking about the 5 volt
oh,
only.
I see. Okay, so 5 volt. Let me just bring. So maybe I'll just share. Sorry.
So it's going to be the questions will be, and like the follow up thing will be like it can be asked like what is going to be the characteristics curve, what will be
Right.
the reason of in both the cases, and the third thing is uh, again yeah, so noise margin and means VIL
Right.
VH, that's dependent over all these things only.
Yeah, so let's say it's a 5 volt supply, so in CMOS. So basically this one remains till 1 volt and this will till 4 volt it is off, right? So this is ground and this is VDD and then you have this. And if your sizes is such that, so let's say Kn is 2 times Kp, well, actually I should write it as mu n mu p. So let's say your mu n is equal to 2 times mu p and your Wp is 2 times Wn, then obviously this will just pass through VDD by 2, right? And the noise margin low and high will be pretty symmetric. So for example, your noise margin low, let's say noise margin low, first of all, it has to be greater than 1 volt because VTN, VTP is 1 volt. So 1 plus some amount. So let's say this is a 5 volt supply, this is 2 volt, let's say. Then given the above condition, your noise margin high is obvious, most probably 2 volt as well. And you have this transition region of 1 volt. Okay.
Yeah.
And if you have a 3 volt one, well, 3 volt one, that's a tricky one. So you still have 5 volt. So you're going to get a dead region actually. So you start with 5. So till 3 volt, this is stays on. And then this one stays off till 2 volt. So this is your dead zone. And then what is this? This is a hysteresis, I guess. Okay. So is this what you wanted to discuss or
Yeah, so I
what?
wanted to discuss. Yeah, I never tried with respect to the waveform, like input output characteristics curve for especially the 3 volt scenario.
Yeah, so I think
So
there'll be hysteresis. Yeah,
so basically what happened, like if you will just draw a normal inverter. So in case
right.
of a inverter, I want to discuss with everyone like, okay, what is going to be happen, and which one is good, and what is the advantage, and where exactly is the advantage and disadvantage.
Okay.
So like,
Actually, if
for,
you want, go ahead and you want to share and show something, or
yeah, miss,
yeah,
I
go
can
ahead.
do it. Maybe, sir, I think you have to stop your
Oh
screen.
yeah.
So what I want to discuss with all of you in terms of you have to give a thought process. Like, don't always assume like, okay, you will get everything at least in the interview and on the company in the same way. So it is like VDD, input and output. This is the thing. So now all of us know. So till now our how MOS, NMOS and PMOS are working. So for NMOS we know like, okay, if this is a VTN and this is VTP and this is your gate voltage. So we know like, okay, if VG is greater than VTN, so that means your NMOS is on. Now when we are talking about the PMOS, so in case of a PMOS, you know pretty well, like, okay, if it is if I'm saying you can say like, okay, VDD minus VG, and that's greater than VTP, then we will say, okay, the PMOS is on. So so the thing is like, okay, if it is 1 volt, this is 1 volt. So what I'm saying, okay, if VG greater than 1 volt, your NMOS is on, and when your VG is greater than 4 volt, then you will say like, okay, your PMOS is no. So
So VG is less than VTP.
yeah, so yeah, so I think I just made a mistake here. Mm, 1 and 0. So VGS, it is 1. Okay, I become confused. So it's like when there is a 1 volt, then uh, NMOS is on, and PMOS is going to on when I have this thing. I can say like VG is on when it is a less than 4 volt. Am I right? Just correct me if I'm wrong.
Yeah, that's correct.
So what is happening right now? But so if you will, if I will summarize these this particular part, so you can see like, okay, in a scale of 0 to 5 volt, after 1 volt, your NMOS is on. Okay, and if I will choose another one, that means below this, my PMOS is on. And just because of this, what is happening, this particular portion, both are on. NMOS and PMOS both are on. So what is happening like when both NMOS and PMOS on? So you can see like, okay, there is a current flowing from VDD to VSS. A large current will flow, and we usually talk about like, okay, there is a transition, and in this transition there is a lot of transition power. That power is going to dissipate a lot. There is another condition, and in that condition, what I'm talking about, VDD, same VSS. I think someone also, someone else also have this using this board. So this, in this case, now let us suppose VTP is equals to 3 volt and VTN is equals to I would say again 3 volt. So minus 3 volt and 3 volt I'm talking about. So you can easily say like, okay, on a scale of 0 volt to 5 volt, again same thing, like after 3 volt your NMOS is on, and 5 minus 3, that means this is a 3 volt and this is going to be my 2 volt. Before 2 volt, this is going to be my PMOS is on. So uh, what about this particular reason? In this case, both are off. NMOS and PMOS both are off. So now from the power perspective, if I will talk about from the power perspective, you can see like there is uh, because when PMOS is on, then NMOS is off. When NMOS is on, then the PMOS is off. So from this, you can easily figure out. So that means there are going to be as such from the current point of view, there are going to be no current from VDD to VSS, because the way we have changed our VTN and VTP, that is on a higher side. Are you getting my point? Anyone have any confusion?
Yes, sir. But as we are increasing the threshold, the speed will be going to decrease.
That's okay. That's okay. So I'm not talking about the speed right now. I'm just talking about whether are you able to understand like whether we can increase the VTN and VTP, and
Yes, sir. Yes.
what is the advantage of that particular part? Any
Yes, sir.
okay. So sir, um, for this particular scenario, this the 3 volt and minus 3 volt thing, I never tried it, frankly speaking, that how is going to be the characteristics curve, and how
Yeah, actually, I showed actually the static curve. I showed it as slowly going. Actually, what I wanted to show was that was a dynamic curve, because I think statically what will happen is you get a hysteresis. So you just get on. So you go from VDD to 0, and then you go to 0 from VDD, but there is a dead region. So like when you're going from VDD towards ground, you'll see the PMOS take over after some time, after 1 volt. So, in my graph, I showed as if it is like two inverter characteristics, right?
yes, yes,
But I think you'll not get that slow, because none of them are on both the time, like as you said.
yes,
So what will happen is you'll get VDD all the way to 3 volt, and then boom, like 2 volts when the input goes above 3 volt. And on the way back, because you have a capacitor charged to VDD or ground, discharged to ground, then the PMOS doesn't go on till you get to the 0.2 volt, and then the PMOS just takes over and charges it up all the way. So it's just dynamic power, like as you're saying. So static character. So I guess this will be interesting. I've never tried a high VT device, but so if you do a noise margin, that'll be interesting to see how the noise margin. So this one, I think your noise margin will be higher than the supply voltage. Like I had explained before, that the noise margin condition is NMH plus NML is lower than VDD. That is only if the VTN plus VTP is less than VDD. If it is not, then the noise margin I think will be higher, because in the first case, your input is considered as a load till you get to VTN, which is 3 volt, right? And then on the higher side also, Uh,
So somehow, when it comes to the noise margin, I think in
well,
this particular scenario, we cannot link in that particular way because this is I'm just talking about from the input perspective. Like
no,
okay, from
well,
the
I mean, the noise margin definition is system-wide, right? So you don't have to know what the structure is. You just have to tell that when the input is high,
yes.
how low can I go for it to be considered as a high?
So so the point is like if you remember in one of the class, I have discussed the same thing. Like okay, and I usually talk uh, understand the noise margin in this particular way. So if this is my output side and this is my input side, so how you're going to define the noise margin? First you have to see what is VOL and a VOH, and similarly sorry,
VIL, VOA.
VIL and VIH and VOH and VOL. So so this portion we are talking about, this difference. Now in this particular scenario, what is going to happen? Like first we have to see like okay, what is going to be my VOH and VOL. So as now if you will see from this 3 volt and the 2 volt, now my log from the input point of view, so that when I'm saying the input point of view, I can say like okay, this is my logic 0, this window. If I will consider this as my logic 0, and this I can consider as a logic 1, and how the output is going to work, that is like whenever the logic 0 is there, then PMOS is on and the PMOS is going to charge, and then
So,
again
so Puneet, I think there is an overlap, right? So the logic 1 you have shown goes all the way to 2 volt, and then the logic 0 goes all the way to 3 volt.
uh, sir, that's thing. So like from the input, okay, so that maybe I'm confused in that particular way because I'm not sure like okay, in this particular case why we will say like okay, from the 2 volt to 5 volt there is a logic uh, 1, because the logic 1 is basically
No,
when
yeah, but
NMOS is
because,
NMOS is on. Basically, I'm just talking in terms of like whether NMOS is on or NMOS is off. So
right.
like if I will see from this, my NMOS is on. Whenever my NMOS is on, I will say like okay, that's my logic 1. Now if it is after 1 volt it is on, then I will say like okay, my this is after 1 volt my logic 1. And if in place of a 1 volt, if it is a 3 volt, then I should say like okay, now my NMOS is on here, then this should be considered as a logic 1. So my I would say like my understanding says in this particular way, like okay, whenever the NMOS is on, after that we will say like oh, the logic 1 is started. And if I will think from that perspective, then here logic 1 is on after 3 volt, and logic 0 is below 2 volt. There is no overlap. But when it comes to in this particular scenario, logic 1 is after 1 volt and the logic 0 is basically you can say here. So in the below we can say like okay, because NMOS PMOS is on here, then there is a overlap here, and then we can calculate the VIH VOH in that particular way. I'm not sure how much I'm correct, but that's my understanding, because if NMOS is not on, then we cannot say like okay, there is a logic 1. Are you getting my point, sir?
Yeah, I'm just drawing it here because I think the way the way we define the noise margin is like or at least how it came into picture is like the way I was. So you have your output settled at VOH. So let's say VDD, right? So the question is, so in this case, the VTP is 300. So
So
you don't go, yeah, because your PMOS VTN is 3 volt. Oh, hold on a second. Actually, both of them VDD. So this is on. So this is 3 volts. So till 2 volt, it can come and go. Yeah, I guess it becomes a dynamic logic. I mean, it'll hold the value, but I don't know how they will define it. Basically, your output should not change when it
Yes.
goes from 5 to 2, which I don't think it will change, but it is actually a dynamic circuit now. The capacitor is just holding the value. So if you want to be on the safe side, I guess you say 2 volt. If you want to be on the conservative, I mean, a pessimistic side, you can say the noise margin is 3 volt on the higher side, 3 volt on the lower side. So it is 6 volt, which is higher than the supply.
So basically, my thing was like uh, I
The
never
way, yeah,
I never checked any article or in any book, because this particular scenario is not in any book. So the basic Kang and everywhere, and that may be a reason the noise margin and all those the equations which they have explained, that
right,
is with respect to the normal 1 volt and a -1 volt related thing. But
right,
they are not discussing this particular part. And fortunately nowadays in the industry, people are using the high VT one,
right.
just to decrease this the
Power consumption,
power
right,
consumption one. And I'm not saying like because obviously this is a 5 volt, so it looks like a 3 volt, and it's on a very higher VT. But when we
right,
are
right. But it's
talking
scaled
about
down. Yeah, it's scaled
yeah,
down for lower voltage. Yeah,
when we are talking about the 1 volt VDDs, and the 1 volt VDD is very easy, even
right.
to design a uh, zero point 0.7 VTN or zero point 0.6 or the zero point 0.5. So these type of things are coming nowadays, and especially when it comes to uh, the IP designing, people are doing this thing. So synopsis, they are using these type of cells, but how the input and output characteristics curve, how the noise margin is going to define, as such, I have my own theory, like I have explained you, but
Right.
not exactly uh, any in a book. I never get a chance to see. So I was just curious to understand, like, okay, uh, how we are going to define this particular part in terms of the equations, in terms of the characteristics curve.
Yeah, I mean, when it is overlapping, I guess, I don't know how they define it. Yeah, the NMOS turning on PMOS might be a safer one. So you might call it 2 volt noise margin here. But typically the way I think the noise margin was at least defined from a system perspective was, if I'm holding a zero value, how much noise can I basically, how much noise margin do I have? How much noise can I withhold and the output will not change? And if
Yes.
you look at it from that perspective, I can go 3 volts right below, because the NMOS is not turning on, and the PMOS is not turning on till 3 volts.
Yes.
If I'm on the lower side, I can go up all the way to 3 volt, because the uh, the NMOS on the other one doesn't turn off till 3 volt, and the PMOS is just turned on. So that way, if you look at it, it is looks like your noise margin is 6 volt, which maybe what it is in a dynamic circuit, that's all you care about. And your static current going 0 because it's negative here, right? If you look at it, there is no static current. So, but it's interesting because obviously uh, we kind of don't do this as normal, like digital blocks in analog design, because we don't want dead zones basically,
So
because the
basically, in
capacitor.
analog, mostly you're working in a transition only. So you're so So for you, that curve is very important. So obviously you need a uh,
Yeah,
uh,
we can't use NMOS, PMOS in the because yeah, exactly. We can't
yeah,
use it as amplifier there because
yeah,
your whole amplifying gain term is gone. But even if we use a digital logic, we'll try not to have a high BTP because in typical cases, I don't think it matters as much. But typically, we would say having a dead zone means the capacitor is actually open, and in that case, if something but in a digital case, you can argue that whatever it is, it'll just pull it down or pull it high. So I think even the digital circuits in analog, we can use this. I just never seen it used. Just that speed, like I think somebody pointed out. I think
yes.
Satalvi. So
Just
speed
going to
obviously will suffer.
definitely like from the timing perspective, on a higher VT, obviously speed is a penalty. So you cannot use it in a place where you need a very fast one.
Right.
But sometime we have to play a very uh, like in a trade-off. Like sometime just for the power purpose, we want to decrease
Right.
the power, and timing is okay. So we can use these type of things. So in a wherever we don't want to consume a lot of power, because this transition time, the during the transition, whatever the power, that's playing a very a major role, I would say. From the percentage point of view, it maybe all of you, it looks to you like, okay, it's just a transition power. But think in this way, like there are millions of such gates are there, and if every gate, and if they are just switching on and switching off at some time, then it's going to be like consuming a lot of power. So people are doing a lot of things just to save power. So yeah, so just think about this particular part also. And like sir already explained you, like, okay, how the characteristics curve will be there. So I think you guys have some if you have time, I would say, explore it and just figure out like how the characteristics curve will be there. And in interview sometime they can ask you like, okay, if I will increase the if I will increase the VTN and VTP, then what is going to happen? So what will be the reason of my NMOS and the PMOS? Because uh, till now, I'm just saying on and off. That's all I'm talking about. But I'm not talking about like where exactly is going to be the linear reason, where exactly which one is the saturation reason. So what you guys have to do, you have to just think from this perspective, take it as an assignment, like, okay, and just come up with, okay, and which particular place, which transistor is going to be on a linear saturation in the cutoff region.
Yeah,
So
that's a very good assignment. I was
yeah, so just come up with a solution. Like at least you should know, like, okay, in this particular case, how what will be the equations? Because all the previous slide everywhere, you're talking about VG is greater than VT and all other things. So from the inverter, you can easily figure out, like, okay, which one is a uh, saturation mode and which particular mode. So just take this as a assignment. Just come up like, okay, in this case, this PMOS is going to be on. On means what is going to be saturation, the linear, and similarly for the NMOS also. And uh, maybe you can present in front of us like, okay, this is your finding.
yeah.
Yes, yes. So that's all from my side. So I'm just stopping. Let me just stop sharing. Maybe if you want to share
Okay,
something.
no problem. Actually, since you're in the topic, we can. I just wanted to show us the other reason people use the high VT also. Actually, okay, so this is what I was saying. Okay, that's the assignment, so I'll not change this. um, so the other reason people use a high VT is, if you have a normal inverter, for example, So let's say this was 1 volt, and VTN, let's say, is zero point 0.1 volt, and the input is 0. So obviously, this is VDD, right? And we say the IDN is equal to 0, right? But if your VTN is zero point 0.1 volt, typically you'll have few nanoamps of current, which is for digital, it is a lot. Like maybe depending on the technology, you might have 10 nanoamp of current. If you take VTN of zero point 0.3 volts, and this is exponential, it'll drop to probably like 100 picoamps. You go to 1 volt, this will drop to like 10 attoamps, you know. And this is called the leakage current. This is just, even if your gate is off, because your VDS is large because of the high field, you just have leakage current. So that's the other reason, actually, at least a couple of the analog blocks, when we use digital, we use high VT to make sure if it is like really low power, we operate at a very high temperatures and high voltages, then we choose the high VT because this leakage current also will drop. Okay. Actually, since you brought that up, what I was thinking was that um, okay, so the other thing, maybe we can give that as assignment as well. Okay, so if VTN is asymmetric, let's say VTN is 1 volt, VTP is minus 0.5 volts, because a lot of times you'll get that as well. So all the calculation I showed you, they were actually assuming that VTN is equal to VT, the mod of VTP. That's why, all your W over L sizing was based on how to get it in the middle. But if you have this, like asymmetric one, then how would you change your VIL and VIH, and which direction, how would you size it? So think about that as well, and how your characteristics will change, how your VI will change. And let's say same thing, you keep mu n is equal to 2 times mu p, typical value of 2.5, then how would you size it? So you can think about asymmetric ones as well.
Yeah. So just one more thing, sir. I,
Yeah.
I think you have explained that particular part, but in one of the interview,
Hmm.
just
Which
uh,
part were you talking about?
you already explained this current related thing, like okay, how the current will be in the different zone.
Hmm.
So in one interview, what happened? Like the characteristics curve which we are talking about, this is the input and output characteristics curve we are
Yeah,
talking about
yeah,
from the voltage point of view,
right,
and that is V in and the V versus V out we are talking about.
right.
In one of the interview, they ask like okay, they need a current curve with respect to the input voltages. So that means output current curve with respect to the input voltages.
For an inverter, you mean?
Yes.
Okay.
So
So,
I'm not sure like uh, how many of these students they can visualize that particular part, but a
so
lot of students they become confused when it comes to like IDD current, IDS current, I would say, and
actually, I still don't. So when you're talking about I output, you're talking about I out here or IDS, just still this current.
yes. So actually you're right. So I was coming to that particular point. So there so there will be no resistance here. So there is
Okay.
nothing like an RL, because in our circuit there usually there is no RL. It is either capacitance is there.
Okay, but it is static though, right? We're still doing static analysis or?
Yeah, no, sir. So that's what I'm saying. So
Okay, okay. So
what?
dynamic part, yeah, yeah.
Yeah. So what they just ask you this question, like, okay, what is the output current and the with respect to the input voltage? So obviously the output current is going to be this current. So the sir which the way sir explain here, this is the output current, and in the output current the capacitance is there. So if the capacitance is there, capacitance is going to charge, and then it is going to just initially when it is going to charge, is going to pass the current, and then when it's going to the fully charge, then the current is going to be stopped. So they ask this thing very clearly, like, okay, if input to output is from 0 volt to 1 volt, 0 volt, zero logic to one logic, and one logic to zero logic, if you are moving like this, then what's going to be the diagram of your
Oh,
output
current
current,
through
I
the
out?
capacitor. I see.
Yes.
Yeah.
So I think, sir,
But
if
I actually didn't talk about dynamic. That I was thinking. Actually, you've been covering the timing part, so I don't know even if I want to cover it. So when I
so
was
I
thinking
think these,
dynamic part, so today that's why I started saying no
yes.
capacitor, right? Static.
Yeah, so I,
So,
I think now all of these people, they know very well like
right.
what exactly we're talking about. So this can be as a part of the one of the assignment for these people. And
Sure.
I don't want just to feed you, spoon feed you, like, okay, this is going to
Right.
be there. I think now you know very well, because we have already discussed, like, okay, how the capacitance going to charge, capacitance going to discharge, logic 0 what is going to happen, logic 1 what is going to happen. So I think you guys can uh, draw easily, at least a waveform you guys can draw, and just
In fact, I was thinking just the dynamic part, just give some assignments and let them do it. Like as you
yes.
said, it just plain RC solving KCL, KVL. So there is really not much different there. So I think they should. Okay, there's some questions. Okay, Subham, you raise your hand. Go ahead. There is a Chandan sent on chat window. I'm
So,
just reading it. Yeah.
can you draw the voltage star VTC for 3VT once again? So I have to
No,
simply
that's your
check.
assignment, right? I was
No, sir.
about to draw,
Uh,
but that's your
sir,
assignment.
but I think in between 2 to 3 volt, the PMOS will be off.
So that's your assignment. Just draw it and send it. Yes.
So
Yeah.
if we go increasing 1 volt by 1 volt and at 2 volt, the PMOS will be off.
Subham, that's everyone's assignment. What are you asking? You're asking to solve it now?
Yes, sir.
No, that's
No.
the assignment, right? He gave an assignment to everyone. Just try it and then put it on the discussion. Yeah, whoever solves it, or just wait for some time. Let everyone think about it. Yeah, I was about to show you. Even I have to work it out, but just try it out.
Sir,
It's
in
a
between 2 volts, 3 volts, there, no one is operating.
Yes, Shubham, no one is going to operate. So, but that's what I have mentioned. Think think about this. If it is not operating, then what is going to happen? Okay, and just
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 think
come
about it.
away.
Let
Yeah,
the other people think about it too.
yes.
Okay.
So
I
I
might give an answer, you might give an answer, but then that'll kill everyone else here. The whole idea was, Puneet said, this is something which you won't find in the book or anything like that. So it'll force you to think, because anything in the book, you just open up the book. So it's a good assignment problem. So think about it. If you know the answer, just we can discuss it later once people have started thinking and working on it. That's an assignment. That's why it was given as assignment to you. Okay, Subham. Or are you saying between 2 and 3 volt, no one is operating, nobody's brain is operating? That's why we have to answer. Is that what you're saying or what?
Sir, we have to draw the VTC or
Yeah, draw the
what
VTC.
else? Okay, sir.
Just draw the VTC, whatever you can. Okay,
Shatabdi,
so yeah,
Shatabdi,
go ahead.
Shatabdi is
Actually,
also asking
Chandan
something.
had a question. Let me just read it out.
Okay.
He's got it in a long time before. I've just So during saturation, I is constant. During cutoff, I equals to 0, and in linear, it will follow Ohm's law. Output current versus input voltage characteristics. Okay, when I say linear, typically in the book you'll say, I don't know what the question is actually. In the linear, yes. Actually, Chandan, can you
Sir,
go ahead and
ask the
answer the?
question.
Yeah, yeah.
Sir, ask
What's
the question that we have to draw the current versus the input voltage characteristics. So
Yeah, but what Puneet is
that
talking
I,
about is the input-output current characteristics of the entire inverter, not the MOS.
so on this basic idea, can we go like in saturation the current will be constant, so it will behave as a current
Yeah,
source
yeah, and yeah, of
and
course you can do that. The only thing
cut
I would
off.
warn is
That's it.
you've asked that in the linear region it will follow Ohm's law. That is only for small VDSs, just to approximate and make your life easier. But if it is not small, then you have to use the nonlinear equation, which you can't obviously use Ohm's law, right? Ohm's law is for only for a linear resistor. Nonlinear resistor Ohm's law is not applicable. You have to apply the square law.
Okay, sir.
So, sir, I think
Yeah,
we can add two more thing here in a current thing. So
sure.
input voltage. So input voltage versus output current. So the output current, now I need two output current. One which sir has mentioned, like this is the output voltage. Another one is VDD to VSS.
Right.
That particular output current, which we usually say IDD current. So yeah,
Yeah,
so
let's say ID, sorry. Yeah, so you want IDD and I out, right?
yes,
For V in. So V in versus IDD and I out.
I think this if you guys can draw these particular characteristic curve, I will consider like how MOS is operating and the equations. So I from my side, right, first you should analyze, you should think like okay how the curve is there. That's should be your first thing, and then come up with the equation like okay within this particular reason this is going to be my equation. So it's going to give you a very good idea about all the equations and everything plus the curve also. So you can do in the both the way, like from the equation how to draw a curve, or if you know the curve, if you can visualize the curve, then how can you explain the equations. So in interview always remember, maybe you can solve it and you can think about this particular part and you can come up with some very fancy curve. I'm not expecting from you guys just to give me a very fancy curve with the basis of the equation. I want from all of you to think logically first without keeping equations in mind, just with the help of some voltage thing like okay, when PMOS is going to be on, when NMOS is going to be on, in which particular reason, what is going to be the curve, and accordingly just draw a rough diagram, rough thing. And I just want to see like okay how much you can visualize, because in an interview they can ask you like okay just can you just draw a curve as per your understanding, and there they will not give you much time like okay you just write all the equation, just solve that and just then come up with a particular curve thing. So you think in that way also.
Yeah, I mean, I couldn't agree more. Actually, I would say don't even think about solving with equation,
Yes.
because as we have seen, like even with two transistor we can get confused very easily, right? So you shouldn't be using equations like Puneet is saying. You have to first find the nature of the problem and nature of the curve and nature of voltages and so on. So for example, Chandan, like as you said, saturation, it's like a current source, and you have the CL, right? So if this is a current source and you have a capacitive load, how should this voltage look like, right? So for that region of operation, you say, oh, this is linear or this or whatever it is. And then you said, oh, if it is in linear region, can I do a small resistor? Yes. If the voltage is really small, then it will look like. And now you know how a RC responds. You know the final value, you know the initial value. So you can do that part like that. So I would say, I don't care about what the final value is, what's the initial value. I mean, the final value and the initial value, but I don't care exactly how the equation look like, but the nature of the curve should be explainable from these type of approximations. I think that's what Puneet, you're
Yes,
saying,
yes,
right? Yeah,
yes, yes, sir.
yeah.
Because see, guys, what is going to happen? Uh, uh, I'm going to ask you. So, at the moment you will come up with a particular curve, what and that's the reason I said like, okay, you have to present it. And so present it in the sense you have to come up with the curve and you have to explain me how. And in the
Right.
explanation, I don't want like you just say like, okay, this is the equation, and
Right.
I solve this equation on the basis of the equation, this is the curve.
Right.
So that's not I'm expecting. I will tell you like why. Because if for the inverter you can easily figure out the equation, but what is going to happen if I will say like, okay, now what is going to be the current in case of AND gate or the NAND gate? So after the inverter, if you will explain me with the help of the equation, that the next question I'm going to ask you like, okay, for the NAND gate, just can you explain me for the NAND gate? And definitely like today's session, the next time when we are going to meet, I can ask you like, okay, can you draw a input and output characteristic curve for a NAND gate? Now that's going to be a tricky one for you. Like, okay, how you're going to explain me? Like, okay, if I will say like, okay, you just draw that particular part, then you will say like there are two input. How we can draw it? I will say like, okay, just consider one as a zero. One input is zero, and now draw it. And then in the second case, okay, consider the input as a one, and then draw it. So basically, what I can twist the question any point of a time if you're going to give me the correct explanation just to understand whether your understanding is correct or not. And this characteristic curve everywhere you will get in a book, and it is with respect to the inverter. But how many of you can draw a characteristic curve of a NAND gate when one of the input is 1 and one of the input is 0? Then you cannot say like, okay, now there are two input, how we can do that particular part. So think from and from that perspective, like if your concepts, if your uh, understanding is good, then the runtime interviewer can twist the question in any direction, and then you can answer it very well. And I'm not saying like you have to give me a correct answer. I am going to see what is your approach. And that's a very key point when your seniors they were interviewed, and uh, the guideline was also in a same fashion. Like, okay, we want, so the synopsis specifically mentioned like we want to see their thought process. If in the runtime, if we will twist the question, whether they are able to approach it correctly or not. And people did it very well. And I think Sarosh sir got a feedback like, okay, at least people were able to understand the question, the runtime. They twist a lot of things, and they were just seeing like whether you're going to the right direction or not. So from the interview perspective, always remember, interviewer just need some time. Interviewer are not expecting the correct answer. They just want to see like, okay, what is your approach? That approach can be right, that approach can be wrong, but at least you are trying, and you're applying your brain, applying your concept. And that's what we want to see, uh, what is there. So like you can see like me and the Saru sir discuss a lot of things on the runtime. A lot of places, even we don't know a lot of things, but just because of the certain background, we came up with these curve equations, because it looks like, okay, yeah, this should be the answer. Even we have to say sometime like, okay, we have to go back and we have to check it. So you can also do in that particular way. Yeah, sir. So that's all. I just want to pass a message like, okay, in the CMOS after this, at least they should have a
Uh,
everyone.
yeah, I mean, again, I couldn't agree more. So, um, I keep telling this that you always have to boil everything you're understanding. You have to boil it down to simple concepts you understand, not what I understand. And, and as you have seen, like even when Puneet said that, oh, inverter, you can write equation, but you just saw, right? The last equation was this big messy equation with a V out in that. This is two transistors, right? You write equations in it, you'll just get lost, in 2 minutes. Like one of my favorite questions in analog interviews is, and everyone complains about it, it's just a C and a R, right? I asked them to draw the S domain transfer characteristics for it. Now, anyone who's done like sixth grade math will be able to do it. But the problem is your problems are not that simple in life. They're not even like close to it, right? Very complex. So you have to do it by inspection, like intuitively understand how did that curve come in. And when I put it that way, then like more than half of the people get lost. And but that's what you'll need to be in a good if you're going into a good corporate environment, because you just can't use equation after. The reason we follow equation is just to give you on what principle it was based on, so that when you're writing paper or explaining something, it is easier to explain it. But if you want to understand, then through the equation you'll just get lost. Like half a transistor, forget two transistor, I can put half a transistor in such a way that you'll get lost with the equation. So you have to boil it down to very simple forms, which you understand, like current sources, capacitors, resistors, capacitors, and this, and then you'll be able to understand it better. Like the whole VTC, right? I've been just kind of alluding, like how do I shift it right? How do I shift it left? What should be my minimum? Like for example, you do the VIL calculation, but let's say I tell you, like give you a number. Let's say VTN is 1 volt and VTC is 2 volt, and I tell you that VIL is 3 volt. Is that valid? Is that correct? You should be able to tell that like in a fraction of a second, right? Like, oh, no, 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 that's not true, or yes, it can be, or whatever it is, right? So you should have that feel completely, not just like the equation, because the equation you'll get lost very easily. And there are some interviewers who will question you that way, but not in a good company. Like Synopsys will, or Intel or Qualcomm's, they will not interview like that. I mean, they will get inside your brain. And like Puneet was saying, when I interview, I don't care about the answer at all. I don't care if he gets the answer or not. I just want to see, like, how did he start? How many words he was using to describe. I think I said that in when Subra was giving the like. A lot of times we sit together. Usually 8 or 9 people will interview one full day, like 10 hours or something. And then a lot of times we just say, "Hey, he just took too much time explaining it," and that's why I keep emphasizing so much that you have to be very precise and to the point when you're answering. You cannot have, I think the example I was giving when we were training people for synopsis is that, how you've probably seen in movies, you obviously haven't been in a criminal court, but how they said everything you say will be used against you. Interviews, not only interviews, even normally when you're asked questions like that, you should treat it that way. What I mean by that is, you should not put in any words there which is not necessary, which can be used against you. One example I'll give you is that, one of the Subra, actually, it was Subra. When we were doing mock interviews, she was obviously nervous, but we asked something about latch up. And obviously, she had a very wordy answer for it. And she threw a lot of terms. Like, for example, she threw SCR, but she didn't know what SCR was. So, first thing, you put in a word which they don't know. Second thing, I mean, is not necessary. Second thing, you don't even know about it. So, because you say SCR, immediately the interviewer is going to just stop there and ask you, what's SCR? Can you draw the IV characteristics of this? So you just dug a hole for yourself. So that's why that whole exercise of I'm asking you, put it in 5 words why you did iteration for that solution, is exactly for that. Because once you start thinking that way, you'll just remove all the unnecessary talks, unnecessary terms, unnecessary everything, and you'll just boil it down to the very necessary thing. I was just telling Santanu that that a lot of times people say, oh, his English is bad, that's why he couldn't answer. um, Let me tell you, you may not know English at all. So I've interviewed, like, I don't know, hundreds of Chinese people actually. I mean, they literally leave the country without knowing English, or maybe one day before, or they just started learning English in the plane. I mean, that's how bad they are in English. But some of the best interviews I've had is from them, because they just use just few words, because they use the language of engineering and to the point, and they just get right to it with just minimum amount of words. So sometimes the English can be hindrance, because you're just telling a novel, you're telling a story there, which is not necessary. You just, because we are engineers, we don't need a essay for us to know what you're saying. You just have to get to the point as quickly with minimum words, but at the same time not confuse them. But you have to be very precise and comprehensive about it. That's why I keep iterating that your presentation has to be good. Like, in our project, I keep saying, when you're presenting, how you present, what information you should have there, because they all reflect how you can communicate your idea. Because you might have the greatest idea, if you can't communicate, it's no good. Same thing with interviews. You might know everything, if you can't communicate it, the interviewer has no idea. I mean, he's not going to take my recommendation or Puneet's recommendation, right? It's their livelihood. So they're not my uncle's company. Even if my uncle was there, he probably won't care. That's why I say you just have to be very precise, very clear about what you're doing. So, and that's why it's very important for you to understand all this in very simple terms you understand, so that you can explain it to people, not with equations. I mean, obviously we have a lot of equations, because it's a way of compressing things which you have learned, and plus it allows you to read material and understand it too. But when it comes to understanding, it has to be intuitive understanding, because with equation you'll just get lost very easily, very quickly. Yeah, I think I'm just like reiterating what Puneet is saying. So just take that into account. Okay, anything else, Puneet? I was planning to just tell them a little bit about the VTC curve of complex gates, but I think let them think about it. I think I like that better, because they know everything they need to know. Let them think about it, and maybe we can give them some assignment problems to think about
Yeah.
it.
So, sir, till now, what is the assignment which you are giving, that they have to just work and they have to come back and they have to submit?
Right,
I think we are not asking them to present in front of everyone. Are we
right.
doing that particular part?
No, no, no. That was for just for the project we are doing,
Yeah.
not for the course.
So
Yeah,
maybe for the now, from the CMOS perspective, maybe at least the couple of assignment uh, you have to like today assignment, you have to come back and you have to present. So that is going to, and who is going to present that, we will choose on the runtime.
right,
So first you have to think about, you have to submit your assignment, and then after that you have to present. You have to explain that particular assignment, like okay, why that particular curve is there.
right,
So that, I'm not saying like okay, you don't discuss with anyone else. You can discuss it. I know like you're going to ask, or you're going to copy the assignments. I'm okay with that. So maybe someone, maybe two or three people can do the assignment and they can explain you. I'm okay with that. But if the moment I'm going to ask you, you should know all the answers. You should know like okay, what is the background, and what is how you're going to explain it. And if there is any cross question, so you should be able to understand like okay, the same concept you have to apply in that case also. So it should not be like okay, you are able to explain me the this particular id curve with respect to VIN versus IDD for a inverter. You were able to explain me that particular part, and the moment I ask like okay, for the NAND gate or AND gate, or just there are two PMOS in parallel or the series, now explain me, and then you are like okay, you don't know. So
yeah,
that's the thing. I think just keeping those things in mind, understand the concept, present in front of everyone. We just want to see how you're going to explain it. It's going to help you in a multiple ways. It's going to help you clarify all of your concepts. You will figure out like okay, whatever sir explained you in the last couple of weeks so well about CMOS, after that are you able to apply all those concepts there or not? That's going to help you in that particular way. It is going to boost your confidence. And the third thing is going to prepare you for the interview also. Because the runtime, the questions which we are going to ask, even we don't know. We don't have the set of questions. Based upon your explanation, we are going to ask. So, sir, I think the couple of sessions maybe we can do uh, in that particular way. Maybe one
Yeah,
day.
and I was thinking, like I was just about to say, I don't want you guys to get intimidated or not ask questions, but every time you ask a question, we cross question, just kind of treat it as an interview question in the sense that, don't get afraid that, oh, I'm not going to ask a question because there will be it is like what Puneet said, it is for your betterment, because when you say, oh, in an interview, how will I answer this? Then you'll slowly start your process of getting it clear and getting that clarification and all that as well. So it'll help you. So I don't want you to get intimidated and not ask anything at all. That's not the purpose. The purpose is like, if you ask us, we cross question you or something like that. You should also treat it as like an interview question. Like, okay, how would I answer this in an interview so that it is clear? Like, just don't, generally throw some guesses out there or something like that. I mean, you can, but do a calculated guess basically, like what Puneet is talking about. We don't know what situation will be, but you mentioned something and we thought of a cross question. We put it back to you. Obviously, you don't know the answer, but how well can you come to a calculated guess? And that's what most interviewers are looking for. And because you brought up assignment, Punita, just one more thing. The assignments are submitted, most of them horribly. I mean, when I say horrible, I mean, I really don't want to. I mean, it's poor Shantanu who's doing right now. I mean, you just scribble things and put it there, right? I mean, what is this? We're not trash cans, right? So what I mean by that is, like, when I present something, do I present you that way? I don't. I just give you the information I needed, and I say this is what it boils down to. So you should write your. I mean, they're simple assignment. It takes 4 lines to write. So whatever scribbling you do finally, but when I'm asking you something, just show the necessary steps so that we know that you're understanding it. That's all. I mean, sometimes it's a 2-line answer. I get 2 pages. I don't know where the answer is, and I'm just looking for it. And why are you submitting those? And so just make sure you're making it legibly correct. And the copying part, like Puneet said,
Yes.
it's fine, but it's not helping you. At least if you write it in few simple steps, saying that this is what I know. I don't care about the answer, like I said. This is what I know. From here, I don't know. I would love that, because then I know that, okay, half of the people didn't understand uh, what the body effect was for the threshold. If you just copy all the 10, I have no idea. Then you're going to blame me after when you don't get the interview. Sir, I did very well, but I don't know why I didn't get the job, which is I hear a lot of times.
So, Shantanu sir, and
Sir,
I will recommend, like, okay, let them submit assignment as they are doing, but
yes.
one day just ask them, like, okay, explain this assignment randomly. Just ask anyone. So then I am 100% sure, like,
Yeah.
if we will just repeat this exercise 2 or 3 times, then definitely, even if they are copying, they will make sure, like, they understand, like, okay, each and every step. So, means I usually do in that particular way. Like, okay, if you can explain me, then that means this is your assignment. If you are not able to explain me, then that means you don't know anything. So that's the
Yeah,
best
I mean,
solution.
No, by seeing, just within 5 minutes, I can understand who copied from that. But I already warned them. But if they,
yeah, I mean,
yes,
first of all, I don't understand why you're copying. Maybe you're thinking by just copying, I'll understand it, which is even if you do that, at least see it and then say, okay, now I'm going to just do it from memory. At least if you do
yes,
that, I think you'll understand it a little bit rather than just copying it. Because this whole idea is like, we also want to know how many people are just way behind.
yes.
It's not like, okay, if you copy it and show it and we are just going to tell Intel that, okay, you got to take this guy. It's, we have no say in any of those. You're going to get interviewed. So, it's like I tell about design reviews. So in analog, design, we, or even in digital, people do that. We do design reviews before fabrication. We do a lot of design reviews. Some design reviews runs for days and days and days and days before we send it out for fabrication, because it's not like software where, they find a bug and fix it and send another revision of it. Here it'll cost $1 million to, if it is at 28 nanometer, it'll cost you this thing. Now, what I'll see, a lot of people, they get very, very, what do you call it, defensive when you ask questions about them in the design review. They're like, oh, no, this I have done. Why are you asking me this? And I tell people, like, what do you want? You have an ego right now that, oh, I've done it well, don't ask me. When the chip comes back, they find that your circuit has a bug. Okay. You lost your job because they're going to spend $1 million. I have, in my entire career of 20 years, whatever, 12 chips, first time functional. I've never had one chip come back and done it. The reason is because I expose myself like to the very detail in the design reviews. Let them rip me off, let them insult me, whatever they want to do, because I don't want to get that chip back and not working, because that's worse. But it's never happened that somebody's insulted me or like that, but I just expose myself. This is what I've done, this is what I've not done. So you should treat yourself like that. It's like you should expose yourself as much as you can, because then when you go inside the interview, you're the most confident guy. Whereas you do all this copying, stuffing and stuff that you enter into the interview and you're just exposed. I mean, you're really naked there. I mean, you're so exposed, like you're thinking, I'm not doing this anymore. And so which one do you want? You want to expose yourself now, right now, and just walk into a synopsis interview and crack it, or just try to fool us as much as you can, and then you're just not going to get to that door anyways. But any interview, you're going to be like that. So that's why I said, do it as much as you can. Explain whatever you're understanding. Just do it as much and very precisely, very comprehensively. Just do that. Don't scribble things all over and treat us like waste baskets. That's what it feels like. Most of them actually when I get the assignments. So just takes responsibility. Like, yeah, we can do all this cross questioning and all that, catch you and all that, but honestly speaking, I don't want to do that. That's like parenting you. That's like insulting your parents. I just don't want to do that. So just take that responsibility and do it. You should be able to do that. So all that, this little juvenile and childish things you're doing, just don't do it. That's my advice. We can do all that cross checks and all that, but I would prefer you not do it at all. Okay. So that's all I have for the assignment part of it. But yeah, everyone, please do it. Those assignment problems are chosen very, 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 very carefully. It's not like some problem you do it where you'll get a grade. It'll help you understand. Like the first assignment we gave you, you probably realize now every inverter, every dynamic problem, every RC problem you're solving goes back to those two problems I gave you. So if you've done that properly very well, you would not be asking a lot of questions. So anyways, so that's all I have. Anything else, Puneet, or?
No, sir, I'm good.
Okay. All right. Thank you, everyone. And yeah, we'll the inverter part, we'll send some assignments as well, but please do the first one, especially the problem solving ones. And the SRAM one, yes, if you are, I mean, those are just simple 3 transistor problem. You should be able to do it, but if you need a little bit more time, just ask for, but go ahead and submit the rest at least. But I want everyone to do that. Okay. All right. Thanks. Thanks, Puneet. Thanks, Santanu.
Thanks,
Okay, sir.
thanks,
Thank
sir.
you.
Thanks, everyone.
Thanks,
Yeah.
Thank you, sir.
Okay. Bye.
Thank you,
Thank
sir.
you, sir.
Thank you.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Very well.